So I'm going to continue to study the examples on assembly, and then depending on how I feel after this, I'm going to study some examples that I think is I haven't seen anything yet, but I think is an implementation of type theory on JavaScript, and it's from the guy on this channel here. So I think it's on another playlist that I watch. He shares his GitHub, which has this code. He basically shares the repository. Yeah, I think it's Modern Foundations of Mathematics. So I'm going to spend some time studying the code, and then if I feel like it after this, I'm going to probably just read continue to read this book, and then like there's a bunch of stuff about types. So there's like I think 3 different books that I found so far, and then there's some papers. So I think I'm probably gonna try to study the papers first. So maybe spend like 15 minutes studying this one or reading this one, and then read the papers. Just gonna wait to see if it's streaming. I'm much more interested or focused on type theory now because I think it's very interesting. So I'm going to try to spend. I want to finish the assembly fast, but obviously I think I have to spend time on each example. So because usually going slower is going faster. So I'll put some music for myself. I'll put, I think, 1 hour on the clock to spend on assembly examples. I think I stopped on this one last time, comparison with constant. So in order to try to go fast, I'm going to, I think I'm not gonna think about, probably gonna think about off-stream. It doesn't matter that much. I think I'm just gonna pick some arbitrary ones to put on Anki. Because I think as long as I have like a diversity of concepts, it's gonna be good enough to train. Because obviously it's something that's like it's a continuous process. So I'm gonna have to review a bunch of times, and eventually I'm sure I'm gonna remember everything. So here is basically the same thing as the other examples. So it's putting 40 bytes, which is 28 hex. So that would be, I think this one is, no, this one is x64, so it's gonna be 5 rows. Then moving 5 to ECX, moves the ECX value to the stack, then compares. So I'm gonna try to remember, so jump lower or equal. Now is like the problem with the flags. So I think that the comparison is gonna set 0 flag if if the value in A is 0, and it's gonna set the sign flag. So this should jump either if the ZF or SF flag is set, I would assume. The stats need to see if the value on A is lower or greater than 0. So basically if A is an active value. Or it's the opposite. So yeah, so this is gonna be the else condition, I think. Yeah. So check to see if A is lower or equal to 0. And it's probably, let me open the picture there with the flags on the jump. So this should be a ZF or SF equals to 1. So usually based on what I've seen on the previous examples, it's going to be the else condition. The jump is going to be the else condition right after it happens. So it's kind of confusing because it's testing the opposite. So subtract a from 0. If a equals to 0, it's going to set 0 ZF flag to 1. If it's lower than 0, it's going to set the SF flag to 1, I think. So this jumps on both situations. So this should be the else statement, which is going to be 3 here. So, but it looks like, no, it's going to be the else if, yeah. Because obviously it's going to be if, then else, if, then else. So go to the else if here. And here is going to jump, this is the else again. So it's going to jump if it's not equal. So this is going to be jumping if the 0 flag is 0, I think. Let's see. Yeah. So I think that this is like an easier one to remember is, and I think it's probably very likely that this is the case. So most situations, what's going to happen is right after the instruction, the else statement is going to be the first jump. So it's kind of confusing because it's going to test for like the opposite condition, which is not the way that I'm used to reading the higher level code. Because obviously when you read the high level, you're always thinking about like what has to be true for this condition to pass, because you're going to analyze the code linearly. So it is kind of counterintuitive, but yeah, I think that's usually how it's going to happen. This is something I have to remember. So it's gonna jump to the 4 there. You can see the mouse. So this will be the else condition, which moves 3 to EX and then returns. So this situation is gonna move 1 to EX and then it's gonna jump to the other ends of the thing, because it's basically the return statements. Here, I think I actually repeated this last time, but is I think a compiler thing, like a lack of optimization, because it doesn't make a lot of sense to put these 2 jumps one after the other. Maybe there's a reason, I'm not really sure. But in my mind, it's just gonna take the first jump, which is basically going to the same place as the other one, and it just returns the function. So one thing that I was like talking to ChatGPT here, is that's a lot more clear in my mind how everything works. So like types are topological spaces, and what is happening, like a type is a topological space, and a function is a path between either on the same space or towards different spaces. I still don't know very well like what would be the meaning of a generic type, like a templated class on C++. I think that the templated class or generic types would be like it's like they call it pairing on category theory, which is like putting two different types together, I think. So it's like the intersection of two types when you have a templated class. And the union would be, I don't think the inheritance is union. The union would be like the concatenation of different types. So the way that I'm thinking about it more now is like the stacks. And this is something that I was thinking now. Because like a stack is a reference frame from an observer. So I think that the main reason why the stack is the way that it is because of lack of memory, but I'm not sure. Because it's like also like in the concept of functions, you're gonna have this idea of composition, which is just connecting 2 different functions. But the composition is, and this is the thing that is gonna like depend on the way that you look at it. Because the composition is just gonna be a traversal from different topological spaces stacked on each other. So like the idea, so the question that I was thinking about is why would the function, like does the function have to be a stack data structure? Because the stack creates a tree, but I'm not 100% sure. So like why is the link between the topological spaces, like, why does it have to be the case that the conversion between topological spaces is done with a tree data structure? That's the stuff that I'm not 100% sure. And obviously it has to do with the scope. So I think there is something there, like it is a causal reference frame or something like this. So now I'm thinking much more, and studying assembly is making it easier to understand this as well, because all that the Turing complete is gonna be like the computer is gonna be a machine that uses the registers. The stack is kind of like a, and this is what I mean. The stack is the in between because it's already the stack itself is a topological space that serves the purpose of translating topological spaces. So yeah, I'm not 100% sure if it's necessary to have a stack to translate between topological. I think it's just a function of the the size of memory, but it basically creates a topological space because it's just the same pattern always that's going to be used to translate information from registers to memory. So what is happening during the execution of a program is you are changing the flow of data between topological spaces using a stack. And the bridge between them is going to be the local variables. So the local state and the relationship between the stacks is going to create the flow of the data, I think. So I think that this only works if I have an address, so I have to create two different variables here. But let me see. I think this is not gonna work, but curious to see. So this is one of the most confusing concepts on C++, that when you have these two things here, it's considered an R value reference. So an L value would be a place in memory, so an address, and an R value would be an actual value, which is data. And you can create a reference to an R value by using these two ampersand operators. So I think this is usually done in classes, but I don't remember really well what circumstances would like be useful. But it's like essentially treating an R value, which is the data, as an address, I think. But I'm not really sure if it makes a lot of sense to do this on this context here. So you would be treating 5 and 10 as an address, I think, and then comparing the addresses. Maybe it's interesting to see what happens here on assembly. It's kind of weird because I can't see the mouse sometimes. I wonder, I'm pretty sure you can't, there is no dark version of this. I can use the extension there, but I don't want to do that. So whatever. So these I think are related to the main. So it's gonna allocate space for the shadow store or shadow stack. So 56 is gonna be 6. No, it's gonna be 5. No, 5. Yeah, it's gonna be 6. Actually, not really sure now. No, yeah, it's gonna be 6. Oh, 7. 7. Yeah, 7. because 5 is 40, so yeah, 7. So 7 rows. And here is moving 10 through this offset here, which is 32. And 5 through 36. So it's pushing the values through this stack, which is interesting because it's different than the other one. So it's not using a register to push the values. It's pushing directly on the stack. And then it's loading effective address. Yeah, so I think it's because it's our reference, it pushes them to the stack, and then it pushes the values, the addresses on the stack to the registers. And then it's going to push that to the, it's going to use that on the function, I think. It's very interesting. It's going to compare the address of the two variables on the stack. As far as I understand, load effective address is going to take whatever value you put there, and it's going to get the address of that. So I think it's getting the address from the position of T1 and T2 there, I think. And then passing to the function, and then this one is going to push them to the stack based on the stack pointer, which is going to be at this offset here. So here is putting them behind the current stack pointer because parameters, and here is also putting behind, I think. But it's just a different offset. I'm not gonna focus on the numbers too much because I know, like, I'm just gonna look into the kind of the idea. But it's basically pushing everything on the stack. Then it's moving to the register again. This is another pattern that I've seen on other situations a bunch of times. Like sometimes it does this where it pushes values to the stack, then pushes them into a register. So it goes from register to the stack, then from the stack to the register. I think it's just because of calling conventions and stuff like that. So here I think it's transferring the values from the previous. Yes, it's transferring the addresses to the stack on these lines here. And then on these ones is transferring those addresses to registers again. Because it's the same offset. Then it compares the value of RAX. So it's comparing the value of memory. So when it uses the square brackets, it's going to take whatever value you put there, and it's like dereferencing a pointer. So I think it is comparing the value that is supposed to be located on RAX, which is the value on RCX from the previous one. So RCX would be this value here, T2 36. So it's probably this, yeah, it's this one here. So it would be 5, yeah, because it's the first parameter. So yeah, that's interesting because I think it is comparing the value. So it's comparing the, and this would be the value as well. So it pushes the address through RCX and then gets the value that exists on that place. So at the end of the day, it's comparing the values, I think, from so it's comparing 5 to 10. And then here is probably going to be the else condition. So it's going to jump not equal, which means ZF is 0. Yeah, ZF is 0. So this label should be the else condition, I think, or else if condition. And then the else if condition is going to compare again. So moves. It's comparing the value of AX with RCX, which with ECX, which is RCX, which is the value of B. So it's comparing B to A again. And then it's going to jump if equal, because the jump is the else. So if it works, then it's true. Yeah. So I think that I understand already. So I'm going to go back to the choosing pointers, and then it gets a lot easier over time. So first cos 5. I think I might have to put the address when calling the upper sum. Yeah. Or maybe I have to. So I'm gonna try like this first. So what I was thinking about here is I'm not really sure if it's gonna work if I initialize as a pointer, because I'm probably gonna have to allocate memory, I think, and I don't want to use malloc or something like that. So like if I initialize as a pointer, and then after that I use like the index notation to uh, set the first value of the pointer as 5, but I think that's probably. So I'm just gonna test like this, and then I'm gonna move on to the next one probably. So it's kind of similar here. Second first, just pushing the values to the stack, then pushing from the loading the address. Oh, it's interesting that it's loading the address again. So I guess it doesn't matter from the previous example to this one. It's basically the same thing, because this one is also pointers. But yeah. So next thing that I'm gonna try is dereferencing the A and B there on the check, just see if it's still the same. Because in my mind, they should compare the pointers. So you should compare if the addresses are the same, I think. Not really sure though. Because here, I'm pretty sure it's gonna load the address from this value here. Is the second into RDX. Which is probably 10, so it's moving 10. But I think it's the address of 10. I'm gonna ask ChatGPT. Yeah, so that's what I was thinking. So I think that is gonna load the address of the stack. Effective address relative to RCP places that address into the RCX register. Yeah, so it's loading this address here into the register there. And then loads the address for the other one. So here in the beginning is basically going to be the same. It's pushing from the register, so it's moving the values, the parameters from the other stack frame to the current stack frame. Pushes the values, those values into the register from the current stack. Then it's going to compare. Here's probably going to be the else. So if they're not the same, so the condition is probably checking if they are the same. Yeah, A equals B. So REX would be the value that exists on B, which would be the address, I think. So it's dereferencing the pointer, basically. So it's still gonna compare the values, I think. So I'm gonna ask ChatGPT. I think it is comparing the values, but I'm not 100% sure. Yeah, comparing the values. So let me see if I can do this. And then see if it's gonna change there. This is basically the same. I think that the difference here is using different register. No, it's using the same register, so it's probably the same thing actually. It's still pushing the values. So from this part, I think is basically the same because it didn't change anything. So it's gonna push the pointers through the stack, which are the addresses. Then it should change on this function, but it seems that it's not changing. It's just gonna push the address to the current stack frame, and then it's gonna push the values, which are actually pushes the value, I think, because using this notation here. So I think this pushes the value that is inside of the stack, but the value should be an address, I think, because it's gonna be these ones, which are these ones. Oh, maybe it is the value still. So the value that is pushing here to or moving to the register is the values that it pass from the other function, which is basically going to be 5 and 10 in this case. It might be different if you use the address there, or if you use the ampersand on the function. So it is comparing pointers on the previous one. It's confusing because of the square brackets notation. So the other thing is gonna load the address into B. No, address starting B into a RAX. So the first one compares the pointers, and this one should compare the values, I think. So maybe I'm gonna go back to the previous one, just see, and ask more questions, just see if I understand. It seems that is comparing the addresses on this situation here. Which I think it makes more sense. It makes sense when I think about it on C++, but the assembly there, I'm not really sure how it works. I'm not sure if they do this. Okay, so let me go over this again. So up until this point, I think is pretty clear. So I think what is happening is that is moving this to the stack, to this offset on the stack, which will be RSP plus 36, which is still above the other pointers because it subtracted 56 here. So it's moving this value. It's weird because it's not a multiple of 8. So I wonder why it uses the 36 as an offset. And the second is going to be 32. So first is below 32. Then is going to load the address of the second value. So it's going to take whatever. Yeah, but this is the part that is kind of confusing. But I think what happens is that is loading RSP plus 32 into RDX. So it's kind of confusing because why is it using this value? Like it doesn't matter. You could just load the address directly. It's gonna on the first instruction is gonna be this address here. So I'm gonna ask this to ChatGPT. I think it is moving the value of the address. So it's gonna move the RSP plus 32 and RSP plus 36 into the registers, and then it's gonna use those registers on the other function. Storing the values 5 and 10 on the stack. These instructions stores the value 5 and 10 and offsets first and second on the stack defined as 36 and 32 bytes from RSP. And then these the values 5 and 10 are placed at specific locations. So I think it is doing the first instructions because of the declaration there. That's the reason. Yeah, because I'm declaring them here. So that's the reason why it's moving them to the stack. Pretty sure that's what is going on. So I'm gonna test to see if I pass 5 and 10 as addresses, if it's gonna work without declaring them. But now I just realized that, yeah, I'm initializing first, so it's gonna push. So when you initialize, it moves the values into the stack. This is kind of interesting though, because based on the convention there, if I remember correctly, usually what's gonna happen is that local variables are gonna be at a negative offset from the RSP, because negative is is on top of the stack. So local variables usually are on top of the stack and parameters are below, which would be plus offsets. So in this situation, it would be like it's moving to positive. So it's moving the values to the stack as if they are local, as if they are parameters, but it might be because they are used on the other function. So this might be why. Instructions store the values for and 10 cents. It's not defined. These values are placed in specific location. Instructions load the addresses of second RSP and first RSP into the register's RDX. This means RDX will contain the address RSP. Yeah, so that's what I was thinking. This allows main to pass pointers, blah blah blah. Okay, so on the other one, let's see. So now it's gonna move. So RDX and RCX contain the values of the addresses from the previous function. So it's gonna move them to the stack of this function, to the offsets. And then B and A are gonna be the values of the local variables. So it's moving the values on those locations, just basically RDX and RCX. So basically moving the values of the address. So it's moving the B address into RAX, and then it's comparing RX with which is the value of the address. So it's comparing both addresses because RDX and RCX are the addresses from the previous one. So I think I understand this. So I'm going to see if I can do this. And then remove the assignments. So apparently it doesn't work. On constants. Because I'm moving, because they are R values, so it doesn't make sense to, because you're passing a reference to an R value, so because the R value doesn't have an address, you can't do that. So you have to pass an L value. So let me see if these are one of the most confusing things about C++. Also, this is stuff about type theory, and I think one of the reasons why it's very interesting is because maybe realize that the language is language is actually very important when it comes to programming, which I wasn't sure. Like I had the intuition that types are very important, but I didn't know the terms to think about this. But now I'm pretty sure that, and this is something that like is a very big problem, which is kind of annoying to be honest, because Go is written in C++, so like the language kind of forces you to implement abstractions that are not the best to solve problems. And that's kind of the issue. And I think this is one of the main reasons why I think me and a lot of people get the intuition that C++ is overly complicated. But I think it's just because of the nature of types. It's like a very difficult problem to solve. And usually you're gonna have trade-offs, so it's not gonna be. It's extremely difficult to come up with like the language. The nature of the language is gonna shape the abstractions that are built on top of the language. So let me see if I can think about a way to move stuff. So let me ask. Yeah. And I think this is related to types as well, because it's gonna be. I think the reason, so the way that I'm thinking there is because of the initialization. So it's like it feels unnecessary to put the values in the stack if we're gonna compare the addresses on the other function. So it doesn't make a lot of sense. But I think it has to do with the types, because the types are going to define the structure of the topological space. So you need to uh, but I'm not really sure if you need to. It might be because of the language. And maybe in this case, but I think it matters because of the constraints of the address, maybe. So it comes down to the question comes down to the how the comparison is gonna work. Because if you're just comparing the addresses, then it should be the same, I think. So I'm gonna think about a question to ask you. But the weird thing is that on the assembly there, like, it doesn't really matter what's happening on C++, I think, when like the way that I'm analyzing there, because I already have the assembly code, so I know the final result, what the final result is gonna be. And on the final result, it looks like it's just comparing, using the comparison operator on assembly, which means it's just gonna take the values of the addresses. So if that's the case, then I don't see why it matters, because the value is gonna be like the same. But maybe the type you use, yeah, the type you use is gonna determine. But actually, maybe not, because at the end of the day, regardless of what type you use, it's just gonna be reduced to a number, like an integer, which represents the address. So I'm not really sure why it's necessary. Like, there's probably a way to compare the pointers without having to initialize them first. But I think it is like forced implicitly because of the nature of the abstraction, because of the topological space. And this is like embedded into the rules of the grammar, which is like the language. So even though like on assembly you can do it, because of the nature of the logic of the context that determines what happens, you are forced to initialize the variables. It's more a question about how the language works. I think I forgot to put the timer. Oh no, I put the timer. Also, it's because of the, so it is basically what I said. Like the context of the language forces you to have a type on the pointer, because types are basically this, like the type itself is a context. So it's like, which is basically what a topological space is. Like it's a set of constraints that determine how the fluctuation of time changes data, which is basically what functions are going to be. So like the functions would be time, and types would be space, and computation is going to be the flow of data between them. So it needs to define the type so that the compiler understands what is the topological space in a situation where you can have dereferencing. Like resolving the topological space, because it's going to compare the data at the end of the day. I'm gonna put this as a thing there. Then I'm gonna move on to the next one. C++. This is one of the things that I'm trying to clarify. It's kind of hard to. It's like, how does the language, what is the relationship between the language? And that's the reason why when I study the stuff here, the code, because I haven't found, most of the material is going to be like on abstract mathematics, but it's not grounded into the application. But I'm sure that there are a lot of resources, and there's like some different languages that allow you to define stuff. So I think Sling is one of them. Then have Coq, and have Eid or something like this. And then Haskell is more. I think Haskell is not really for proofs, but you can do proofs on Haskell. So obviously I can think about it in an intuitive way, but I think what I'm trying to clarify is more fundamental, like the first principles perspective of how it works. And obviously, if I think about it, the easiest way possible would be to get the two different types into a lowest common denominator and then compare the exact values. But even then, it's kind of weird. Because at the end of the day, on the hardware, it's going to be based on bits. It's going to be Boolean algebra, basically, the comparison. But how do you determine when it comes to the language? Like the structure of the language is going to impact. I think that's the relationship that is kind of hard to clarify. So what is the relationship between the structure of the language and the topological spaces that define what the language is? Because the language is going to be a finite state machine that has access to this stack. Because this stack is the yeah, I don't remember the name very well, but it's basically what it allows you to create the abstract syntax tree, I think. Because the tokens are going to be a finite state, basically a finite state machine, but I think it's called finite automaton, but it's basically the same principle. And then to convert them, but actually even the tokens, in order to convert them, you need to have a stack, because the flow of the stack determines the range of the states, the transition between states. It's basically the same thing actually, like, because it is gonna be type, it is gonna be category theory as well. The finite automaton is gonna be the relationship between sets and objects on the sets, and the functions are gonna be the translation between the states. So maybe language itself is a topological space. Or you're basically transferring, but then how does it work? It's kind of confusing. So I'm just gonna continue to the next example. And the other ones are gonna take a lot of time actually, because the multiplication is gonna be very confusing. On this one might be, I'm just gonna ask ChatGPT to create a function, because I don't wanna think about it, because I'm sure I can create a loop and then whatever. I'm gonna call it like this. Oh, let's have this. So similar. So this one is a different instruction, but I think it's very similar, just allocating, so creating local variables here, or global variables, I think. I'm not really sure, but so because I seen on assembly that usually when people write, it's different than the one that you get here, but when they write, you are gonna have a section where people are gonna declare strings, but I'm not really sure if they are, because based on the code, they should be local. So it's loading the address of the first character probably on RAX. Then it's moving that to the offsets here. It's also interesting. It's interesting because I suppose that it's gonna calculate the size of the string. I think here is only moving the. Actually, I'm not really sure. As it has to be, it moves the address to the stack, so it probably doesn't move the. It doesn't calculate the value of the string, It's probably gonna do. There are some special instructions on assembly, but I think it's not using, as far as I can tell, here, it's not using any of them. It's gonna call the other function probably. So on this one, but it doesn't show the code for this one. But there are some functions in assembly that use the ESI and EDI register to move strings from one place to the other. It's like a built-in function on assembly that probably does the same operation, I think, from the beginning of a string to the end. So it's used for moving strings from memory, I think. But it doesn't look like, probably this function here is going to use something like this, or maybe not, not really sure. So I'm just going to paste everything. Loads the address. You got the address of a variable in memory. Flat keyword is often used. You are working in a flat memory model. Interesting. Where the entire address space is treated as a single linear address space as opposed to segmented memory models using older architectures. So I think that usually the videos that I've seen on assembly, they're gonna use the segmented memory model, which is you're basically separating the code you write on assembly based on the sections where the code would be on previous hardware architectures, which I think that they changed on 64, but I think it's probably, from what I remember, is after 16 bits, but I'm not 100% sure about the 32, if 32 is flat memory model. But the way that flat memory model works is that you're going to have virtual addresses on the process. The process is an abstraction built from the operational system builds the abstraction that is the process. So the operational system translates the virtual addresses from the process into physical addresses through virtual pages. So it's basically flat, which means that the addresses on the process are going to be directly translated into physical memory through the virtual page. But on segmented memory models, it's going to depend on the segments on the process, because they're going to be divided. So you're going to have some section that is devoted to the heap, some section to the stack, another section for static data, and another section for text, which is the code, the instructions. And the operating system is going to randomize this based on ALCR, I think, address space layout randomization, in order to make a higher exploit. But I think that you can brute force the LCR. But it's just an extra step that makes it harder to figure out the addresses on the process in order to hack. global symbols. So it's interesting that. So I'm gonna see if I create two different strings instead of this one, if it's gonna do the same thing there. Change this to make it easier. But it looks like it's doing the same thing. So I don't know for sure if I understand why. Because it seems very inefficient. Well, obviously ChatGPT could be wrong as well, but I think that's probably correct. Like is creating the strings, here it is different. Also, these ones are global, but actually this is kind of weird. So I think that the offsets here are going to be used on the function. So yeah, these values are actually offsets, they're not the value of the string. So it makes the addresses as global and the variables as local. So the addresses of the strings are global, but when you like the difference between the local variables is going to be on the value that it pushes there. So it's basically the same as the other one, I think. So these are the actual values of the variables that are used to pass data to the registers, and then these are the addresses of the actual string. So the address of the string is global, and it's probably like a C++ standard. So the variable is local, but the string address is global. Because what is probably happening under the hood is going to put this on an address inside of virtual space inside of the process. And these are going to be the relative offsets from the process address. And uses a flat memory model, which means it is not going to segment this. But maybe the thing here, like the string parent determines the offsets. So it's probably coming from the compiler. Yeah, so I'm gonna move to the next example. I should probably start studying the other stuff now, as the timer went off. I'm gonna put this as a one that I'm gonna copy or move through Anki. Yeah, I want to finish this fast, but it looks like it's gonna take a lot of time. I think it's probably worth it to study types now. It's a lot more interesting. Here the main difference. So this one is, as far as I understand, is gonna be 32 bits, and is using x86 on 32 bits. So it's gonna, and it's like a different thing. It's basically the same thing. So sets up the stack frame, then allocates 8 to the shadow space, which would be 2 rows in this case, I think. Then it's gonna use the offsets from the strings that allocates here. Interesting. Yeah, so whatever. I'm going to study this stuff now. I think I'm gonna spend 1 hour studying this, and then I'm probably gonna read the books with Speechify. So I think that this is the first one probably. So both these files I got from the repository there. I don't remember which one it is, but it comes from the channel there that I showed in the beginning. Yeah, this guy. And I think it comes from this playlist here. Yeah, it is this playlist. So somewhere along these videos here, he's gonna, on the description there is a link to the repository that I got the files from. And both of the files are from, like these two files here are from the project here. I just downloaded them because the link links directly to them, I think. But I also downloaded the full repository. So the main thing that I'm interested on here is to understand, to bridge the gap between the abstract stuff on the mathematics, which is type theory, and the implementation of that. So basically, I think on these examples is something related to how to use the proofs on type systems to create a programming language. But I don't think that he does the whole thing. It's just like a very simple example. But I want to try to clarify how it works. So I'm gonna look into these files first. So it looks like it is a React app based on the thing there that I saw. Also, maybe I should do this as well, which is to use npm start or npm install and then npm run. But if there is like problems, I'm probably not gonna spend time trying to figure out how to do it. I'm going to just study the source code here. Like the thing that is very weird about like I'm not really sure if I'm understanding things the correct way because it seems very simple when they explain like the concepts, but like it doesn't mean like anything when it comes to the practical sense of the thing. I think that's the part that I'm struggling to clarify. It's like how do you bring that to an actual thing that you can implement? Because the way that they show is you have two different statements that you put on top, and then you draw a line below them, and then at the bottom you have like a final statement. So it would be like a proof. Like if this thing is true and that other thing is true, then this other stuff in the bottom is true as well. And then you can stack proofs on this. And I think that the translation here is related to this stuff. So this is another thing is that I think he explains based on, so the types are related to environments. So when you have like a lambda, have lambda and then type equals to, lambda in a variable equals to this type, you're saying that the variable is going to have that type in that context. So I think this is related to this. So the kind would be the context, and the rest, I think the name is probably the variable, or maybe the name is the type. The label is the variable. Example type declaration. Sim term one. Oh, so it's nesting the objects here. Oh, so this is the type, and this is the term. So the kind determines what it is. So a term, I think it would be like a variable. So the name would be the name of the variable. So variable A, and then you have the type A. And then you have here the declaration. The value is the term, which is the variable, and the type is the type, which is A. So it looks like there was a, it's probably something related to node GIP, I think, based on the, yeah. So this stuff always gives me a problem. So it is because of node GIP. So node GIP is a library on JavaScript that allows you to build C++ or other stuff. So it's basically a library that is going to search for executables on the computer and then use that to bridge the gap between Node.js and C++, I think, or C. And usually I have problems with this library. And I think it's just because like it's very annoying. dealing with the build system on C and C++, and there's like small differences in versions and stuff like that. This creates a massive problem. But I think here is probably something related to some library or something, which is very annoying. I can't even see the beginning of the error. So it failed when trying to download the 22.9 version. So I think that is requiring to have the 22.9 Node.js version. I think this gets 22.9. So let me see. I think it's Node 22.9. So one thing that I can try is to execute this with administrator privileges, but I'm not pretty sure if it's gonna work. I think it's probably not worth it to try to solve this on string. It's probably better just to read the code there, as this can take a very long time to figure this out. But I think it's a privilege thing, so it's trying to create a directory and can't create. Or maybe not. So I think this problem is like the same I had on when I was trying to build VS Code as well, I think. On VS Code was something to do with the versions there and some other stuff. But I think it's probably like the same thing. So it's trying to execute nodes. And it's the same command that I had the problem as well on the other time. Is the rebuild command. It's something to do with the versions and the way that NodeGip's gonna work. So NodeGip works, uses some Python scripts, I think, and it basically works. So I don't remember really well, but I think each project you need to create a build or like a file that has configurations and a build specification, and then it's gonna use those files from a Python script that NodeGip has, and depending on what kind of command you have, is gonna uses JavaScript to build a not C++, bash command or PowerShell command to find these other executables to build the files, I think. I'm not gonna focus on this. So let me see if I understand what's going on here. So I have judgments as well here, context. So judgment has a context and has a declaration. Declaration has a value, which is the term, and the type. So I think I'm understanding how it works. So you have a context, and then you have types, and you have variables. And then on the judgment is the thing that is going to use the context to see if the declaration is correct. which is basically gonna see if that value is of the type that you have. Probably that's how it works. I want to see how the function there works. So it expects a judgment on both situations. A declaration kinds. So it's checking for the type here. What is the type declaration? But this is the thing that is kind of annoying, because I think it's going to be a recursive thing. Like, because you're using a programming language already to do this stuff, you are already working under the assumptions of the language. So it's going to use the built-in mechanisms that the language has, which is already its own topology. So that's why it's kind of annoying to try to clarify this, I think. But maybe it doesn't matter, because obviously this is a weird thing that is kind of confusing, but it makes sense once you understand that you can bootstrap. Obviously, the first compiler is going to be like bootstrapped from the original. So you start off with binaries, then from the binaries there's a arbitrary subjective translation into assembly, which is going to be the instruction set architecture. And from that point, you can use that abstraction to create a sequence of heuristics that is going to create a language. So you basically build concepts based on a finite state automaton, or finite automaton, and the rules of the grammar, which creates the abstract syntax tree. This allows you to create concepts that simplify the execution of programs. And I think it has to do with Occam's razor on the network. So you're creating abstraction based on the initial instructions. Then you can use those abstractions that you created, which is basically the language, to build itself later. Because it's a recursive thing. So it's probably the same thing here, but it is more confusing to understand, I think. Because essentially each time that you go through this, and I think that's related to entropy as well, because each time you do this, you are increasing the loss you have of information, because you're creating black boxes based on that Occam's razor, which is the symbolic representation of the computation. And that's what creates the arrow of time, I think. So the final is going to be here. So it's passing the two judgments to this thing here, and it's creating a pair. So a pair, from what I remember from category theory, is going to be the intersection of two different sets. So it's just like creating a pair on Python, I think, or either Python or C++, that you would have. I don't remember, like, I don't think I ever used this library on C++. Like, it would be type 1, type 2. And then you can use pair, make pair, and then you pass like int floats, and this, like, you would be, but this, I'm not really sure if this creates A plus B, or like type 1 plus type 2, or if it creates the intersection. I think it creates the intersection, because what you're basically saying, you're creating a new set where the first value is from one type and the other value is from the other type. And this is equivalent of doing the product of the two different types, which would be the intersection of them. So I think that's what they are doing here, based on the product. So they're getting one type, and they are doing the product with the other type instead of this function here. So this function would be a functor, I think. Or it might be just a function. So this has a context and has a declaration. The declaration has, so the declaration contains a term and a type. The term is like the variable. The type is what the variable is supposed to be. The context is what determines, is like a namespace thing. So I'll be right back. So they're both using the same context, I think. Yeah, they both use the same context. And this uses this declaration, which is as a term. So it is like A and B, like two different variables and two different types, basically. And they both use the same context. I think I understand now the relationship between the objects there. Then it passes here. And then it's just creating another object. So just does some checks to see if the structure is correct. Checks to see if the context is the same. Equations are the same. And then it creates another object. Is a pair. So it's a term and a pair. The name is one plus the other. So the first, so this would be like making a pair on C++. You just create the intersection because it's gonna be a new set where the first value is from one type, the second value is from the other. But I still don't understand very well, like what does it mean to do this? I know there's something like deeper here, but it's kind of hard to think about. The type is just gonna be a collection of, it's gonna be, yeah, one and the other. So it's putting the values together. So I think it's pretty easy to understand how it works here. Let's see this one. Kinds of things. Term, maybe variable, which is a value of a type, or maybe a type itself, since we are including a universe stack. Membership judgments like x, a for terms x and a. And equality judgments like x equals y, a for terms x, y, and a. A context, a list of membership judgments. Context followed by membership or equality judgments. Okay, so I have the context here, and here you're gonna have an input. This one's more complicated. Oh, this is a sequence, so it accepts context and 0. Baby universe, have to check level is non-negative integer set to default at 0. So parent universe would be +1. And output. So value is, yeah, I'm not really sure if I understand this. Obviously I understand the code, but I'm not really sure if I understand what it's supposed to mean. That's kind of the problem. So let's see this one. Below implements x86 from page 544 of the hotbook. This stands for homotopo type theory, I think, or homotopy type theory. Basically, if the input sequence has a consequent that is a judgment that a term is a member of a universe, then we can make a variable with a type the same as that of the term. We output such a membership judgment appended to the end of the context of the input sequence. It would be nice to record the times of the terms as they are made. This seems to cause issues when we have an infinite stack of universes. So let me see. So it's passing the first one that I created there with AA. AA is supposed to be variable name. So this is going to be this thing here, I think. Yeah, this thing here. So this is basically creating an object that has this kinds, which is just one relationship between one level and the other, which is just based on this number here. So whatever level, so it starts at level 0 and the parent's gonna be level 1. So I think this might be like a relationship between sets. So the parent would be a set that encapsulates the other one, but I'm not really sure if that's the case. So it's gonna pass this through here. It's gonna see the conditions there. Have to check none of the values of the input context entries have the same name as variables. Should all check variables. It's missing. So you guess the value from the consequence, which is I think this. Oh, it should be this. This is the sequence, and this is the consequence. The value would be this. It's the name of the variable, I think. Input sequence. So this is the context that it passed there. The consequence. Shouldn't the consequence be? The consequence is going to be this one, which is this one, which has the value, which is the baby universe. So this one is the baby universe, the object there. So the baby universe would be the type. And then it's pushing this judgment to the entries, which are parts of the entries on the sequence. I understand what the code means, but I still don't understand like what it's supposed to do with this. And that's kind of the problem. Now it's passing the context from the previous one to this one, and index. I think this call here is just adding variables to the context that you pass here. So this would be adding this x variable to this new context. Or yeah, this it's not context, is this sequence here. This creates the universe, the sequence, and it pushes the yeah. So this function, like I said, is gonna put the variable into the context you pass in the first one. It's not hard to understand the code. It's just like I'm not really sure what exactly it means. Yeah. So I still not sure if I understand what it's supposed to mean. It's basically from this code here, like what he's doing is using these objects to create logic that has the relationship between variables in different contexts. So like the objects would hold context and some extra information that determines what kind and what type it is. And then from when you have the objects, you can compare them. But the thing that is kind of annoying is that you're still like it's not a generic thing because you're still operating based on the constructs of the language. But obviously, so like this is the relationship that is kind of difficult to understand because it's like a recursive thing. I think it's like it's the same problem with knowledge, the epistemology of knowledge, which is you're always operating based on the paradigm that you're using to solve the problem. So like in this case, you're using the topological space from the JavaScript language to create another topological space. It's like this recursive thing, which is a self-fulfilling prophecy. So the hard part is like understanding what is the fundamental principle underneath this and how this is going to be related to creating another language. I think probably I'm gonna read the books now. So I'm curious about. I think I have to clarify more the compiler part. And that's the part that is kind of confusing to understand. I guess the question would be like, does the structure of the language in which you are implementing the relationship between types, if that's gonna influence the final results you get? Like, does the initial compiler that you use to build a new language influence the structure of that language? Because it doesn't seem that that's the case, because obviously after you have the first compiler for the new language, you would be able to use that to change the language. But in a way, you're kind of still. So I think that there is something there that like is can be abstracted away from the language, but the problem is like what exactly is that? I think I have an idea of what it is, but not 100% sure. Yeah, so let me think about whether or not to. Because I thought that it would take a lot more time to go over the code there. Because obviously I didn't look into this before. So, and I think that it's not worth it to spend time trying to understand the React parts. I don't think that this is gonna allow me to clarify the stuff that I'm trying to clarify. Because now I'm mainly focused on the relationship between this and compilers. I think I'm going to study or I'm going to spend some time reading the books there with Speechify. So I'm gonna do that. I'm gonna spend 15 minutes on this one, and then I'm gonna uh, read there's two small articles, and I think I'm gonna finish this book. So I'm gonna do both books at the same time. So this is Engineering a Compiler, and there's a bunch of other books that are related to type theory.
Code into executable form. It faces myriad choices about specific details, such as the organization of the computation and the location of data. Such decisions often affect the performance of the resulting code. The compiler's decisions are guided by information that it derives over the course of translation. When information is discovered in one pass and used in another, the compiler must record that information for its own later use. Often compilers encode facts in the IR form of the program, facts that are hard to read or arrive unless they are encoded. For example, the compiler might generate the IR so that every scalar variable that can safely reside in a register is stored in a virtual register. In this scheme, the register allocator's job is to decide which virtual registers it should demote to memory. The alternative, generating the IR with scalar variables stored in memory and having the allocator promote them into registers, requires much more complex analysis. Engineering a compiler. DOI 10.1016 B978-012-088,478-0.00074. Copyright 2012. Elsevier Inc. All rights reserved. Chapter Code shape. Encoding knowledge into the IR namespace in this way both simplifies the later passes and improves the compiler's effectiveness and efficiency. Conceptual roadmap. The translation of source code constructed into target machine operations is one of the fundamental acts of compilation. The compiler must produce target code for each source language construct. Many of the same issues arise when generating IR in the compiler's front end and generating assembly code for a real processor in its back end. The target processor may, due to finite resources and idiosyncratic features, present a more difficult problem, but the principles are the same. This chapter focuses on ways to implement various source language constructs. In many cases, specific details of the implementation affect the compiler's ability to analyze and to improve the code in later passes. The concept of code shape encapsulates all of the decisions, large and small, that the compiler writer makes about how to represent the computation of both IR and assembly code. Careful attention to code shape can both simplify the task of analyzing and improving the code and improve the quality of the final code that the compiler produces. Overview. In general, the compiler writer should focus on shaping the code so that the various passes in the compiler can combine to produce outstanding code. In practice, a compiler can implement most source language constructs many ways on a given processor. These variations use different operations and different approaches. Some of these implementations are faster than others. Some use less memory. Some use fewer registers. Some might consume less energy during execution. We consider these differences to be matters of code shape. Code shape has a strong impact both on the behavior of the compiled code and on the ability of the optimizer and backend to improve it. Consider, for example, the way that a C compiler might implement a switch statement that switched on a single byte character value. The compiler might use a cascaded series of if-then, else statements to implement the switch statement. Depending on the layout of the tests, this could produce different results. If the first test is for 0, the second for 1, and so on, then this approach devolves to linear search over a field of 256 keys. If characters are uniformly distributed, the character searches will require an average of tests and branches per character, an expensive way to implement a case statement. If instead the test perform a binary search, the average case would involve 8 tests and branches, a more palatable number. To trade, code, source code, XYZ, low-level free address code, R honors Y, RTR1, RZR honors, RZR honorary, RZRTR1 plus YRTR1 plus R, tree, XYZ, RZRXY, RYRXRZ, RXYRZ, figure 7.1 alternate code shapes for XYZ, data space for speed. The compiler can construct a table of labels and interpret the character by loading the corresponding table entry and jumping to it with a constant overhead per character. All of these are legal implementations of the switch statement. Deciding which one makes sense for a particular switch statement depends on many factors. In particular, the number of cases and their relative execution frequencies are important, as is detailed knowledge of the cost structure for branching on the processor. Even when the compiler cannot determine the information that it needs to make the best choice, it must make a choice. The differences among the possible implementations and the compiler's choice are matters of code shape. As another example, consider the simple expression XYZ, where X, Y, and Z are integers. Figure 7.1 shows several ways of implementing this expression. In source code form, we may think of the operation as a ternary ADD shown on the left. However, mapping this idealized operation into a sequence of binary additions exposes the impact of evaluation order. The three versions on the right show three possible evaluation orders, both as free address code and as abstract syntax trees. We assume that each variable is in an appropriately named register and that the source language does not specify the evaluation order for such an expression. Because integer addition is both commutative and associative, all the orders are equivalent. The compiler must choose one to implement. Left associativity would produce the first binary tree. This tree seems natural, and that left associativity corresponds to our left-to-right reading style. Consider what happens if we replace y with the literal constant 2 and z with 3. Of course, x23 is equivalent to x5. The compiler should detect the computation of 23, evaluate it, and fold the result directly into the code. In the left associative form, however, 23 never occurs. The order x, z, y hides it as well. The right associative version exposes the opportunity for improvement. For each prospective tree, however, there is an assignment of variables and constants to x, y, and z that does not expose the constant expression for optimization. As with the switch statement, the compiler cannot choose the best shape for this expression without understanding the context in which it appears. If, for example, the expression xy has been computed recently, and neither the values of x nor y have changed, then using the leftmost shape would let the compiler replace the first operation, r1, rxy, with a reference to the previously computed value. Often, the best evaluation order depends on context from the surrounding code. This chapter explores the code shape issues that arise in implementing many common source language constructs. It focuses on the code that should be generated for specific constructs, while largely ignoring the algorithms required to pick specific assembly language instructions. The issues of instruction selection, register allocation, and instruction scheduling are treated separately in later chapters. 7.2 Assigning storage locations. As part of translation, the compiler must assign a storage location to each value produced by the code. The compiler must understand the value type, its size, its visibility, and its lifetime. The compiler must take into account the runtime layout of memory, any source language constraints on the layout of data areas and data structures, and any target processor constraints on placement or use of data. The compiler addresses these issues by defining and following a set of conventions. A typical procedure computes many values. Some of them, such as variables in an algo-like language, have explicit names in the source code. Other values have implicit names, such as the value i3 in the expression ai3j2. The lifetime of a named value is defined by source language rules and actual use in the code. For example, a static variable's value must be preserved across multiple invocations of its defining procedure, while a local variable of the same procedure is only needed from its first definition to its last use in each invocation. In contrast, the compiler has more freedom in how it treats unnamed values such as i3. It must handle them in ways that are consistent with the meaning of the program, but it has great leeway in determining where these values reside and how long to retain them. Compilation options may also affect placement. For example, code compiled to work with the debugger should preserve all values that the debugger can name typically named variables. The compiler must also decide for each value whether to keep it in a register or to keep it in memory. In general, compilers adopt a memory model set of rules to guide in choosing locations for values. Two common policies are a memory to memory model and a register to register model. The choice between them has a major impact on the code that the compiler produces. With a memory to memory model, the compiler assumes that all values reside in memory. Values are loaded into registers as needed, but the code stores them back in memory after each definition. In a memory to memory model, the IR typically uses physical register names. The compiler ensures that demand for registers does not exceed supply each statement. In a register to register model, the compiler assumes that it has enough registers to express the computation. It invents a distinct name, a virtual register, for each value that can legally reside in a register. The compiled code will store a virtual register's value to memory only when absolutely necessary, such as when it is passed as a parameter or return value, or when the register allocator fills it. Choice of memory model also affects the compiler structure. For example, in a memory to memory model, the register allocator is an optimization that improves the code. In a register to register memory model, the register allocator is a mandatory phase that reduces demand for registers and maps the virtual register names on physical register names. Physical register, a named register in the target ISA. Virtual register, a symbolic name used in place of a physical register name. 7.2.1 Placing runtime data structures. To perform storage assignment, the compiler must understand the system-wide conventions on memory allocation and use. The compiler, the operating system, and the processor cooperate to ensure that multiple programs can execute safely on an interleaved time-sliced basis. Thus, many of the decisions about how to lay out and manipulate and manage a program's address space lie outside the purview of the compiler writer. However, the decisions have a strong impact on the code that the compiler generates. Thus, the compiler writer must have a broad understanding of these issues. Figure 7.2 shows a typical layout for the address space used by a single compiled program. The layout places fixed size regions of code and data at the low end of the address space. Code sits at the bottom of the address space. The adjacent region, labeled static, holds both static and global data areas, along with any fixed size data created by the compiler. The region above. The compiler may create additional static data areas to hold constant values, jump tables, and debugging information. Low, 2n, code static, keep free memory stack. Figure 7.2 logical address space layout. Page the unit of allocation in a virtual address space. The operating system maps virtual pages into physical page frames. These static data areas is devoted to data areas that expand and contract. If the compiler can stack allocated ARs, it will need a runtime stack. In most languages, it will also need a heap for dynamically allocated data structures. To allow for efficient space utilization, the heap and the stack.
This is basically the stuff I was talking about before, about the virtual address space of the process. So as far as I understand, this would be the segmented version, but I'm not 100% sure because I think like it's kind of confusing. I'm pretty sure that that's how it works. On the flat memory model, you don't have the segmented parts here, but I think that's because the difference might be on the like abstractions outside of the process, and that's the part that I'm not 100% sure, because there is a other thing called global descriptor table and local descriptor table, which are the like there is a register that is used to map the addresses on like it's like the name size is like a map, because like an array of addresses on the hardware that are used to map the virtual pages to physical pages. And that's done through the registers that are the global descriptor tables, as far as I understand. But I think that it would make more sense that the distinction between the flat memory model and the segmented memory model is on the virtual addresses of the process. But I don't remember really well. But I'm pretty sure that's how it works. But it might be different. So I think that's on the way you access the data for the process is you're gonna set the bits for the pages, and then you're gonna set an offset to get like the relative position you want for the process. But it's kind of confusing because there's like conflicting information on this topic, depending on what kind of videos you watch or what kind of articles you read. It's like kind of confusing the separation between like this distinction. Yeah, I think that on the segmented approach, you have something called far pointer, which is going to be like extra steps to translate the address from the process into the physical page, because you have to go through these segments. But I don't remember really well. The place that I remember seeing this is on the OST. I think it's Intel architecture. It's this course here. So maybe I have pictures that I took, but it's basically this course. So maybe I'll have to do the course again. Because on this one, he explains the relationship. Let's see if I can find pictures. Oh yeah, I took the picture. So it's basically this thing here that he talks about there on that course. But this is the part that I'm not 100% sure. I think that on the segmented model, you will have this other information here, which is basically the segments. And so what you get is a fire pointer address from the process. Then these registers are used by the operational system to find what the equivalent address would be on the actual physical page. And it does that by going through this descriptor tables here. So the descriptor table accepts the segment information. And then you have these other tables that are used for interrupts or traps or exceptions. So an exception is when something goes wrong in the execution of the process itself. An interrupt is when something wants to demand the execution, like so for example, when you use the keyboard or the mouse, then you have to interrupt the current process running so that the processes that have higher priority run. And once that happens, I think you have to save the current state of the execution of the current process into a stack so that later on we can continue the execution from that point. But basically, I think that's the relationship. So yeah, based on this, just looking at this alone, I'm pretty sure that the main difference is going to be on the organization of the virtual address on the process. So on the segmented model, you're going to have these different sections that determine data for the stack, data for the memory, data for the code, data for the static variables on the code. And on the flat memory model, you're just going to have like the address space of the process. And what's going to determine is what kind of offsets you put there. But this, like, I have a lot of questions, obviously, because of, like, obviously you need to have mechanisms to prevent the stack from being corrupted with the addresses from other places. So obviously assume that there is code on the operational system that is gonna trigger exceptions and stuff like that. Yeah, but I think that's basically how it works. So the linear address space is going to contain the virtual page information, which is going to translate into the physical page. The CR3 register controls or allows you to, but I think you need privilege to use the CR3, so you can't access directly from a user process. And it allows you to access the physical pages by setting the bits of the register. But the question is the relationship between this one and this one. But I think like on the segmented model, you start on the far pointer, and then you use this control register to get to the physical page. So it would be like the segments, then the global descriptor table and local descriptor table, then the linear address, which then translates, the linear address contains the virtual page addresses, which translate into the physical page. And on the flat model, you wouldn't have the stuff on the top here. You would just have the linear address and the direct translation into physical pages. I think that's how it works. I'm gonna watch this again probably to remember this stuff. It's probably one of the best. I think it's the one that I like the most of the OS Open Security Training YouTube channel.
should be placed at opposite ends of the open space and grow toward each other. In the drawing, the heap grows toward higher addresses, while the stack grows toward lower addresses. The opposite arrangement works equally well. From the compiler's perspective, this logical address space is the whole picture. However, modern computer systems typically execute many programs in an interleaved fashion. The operating system maps multiple logical address spaces into the single physical address space supported by the processor. Figure 7.3 shows this larger picture. Each program is isolated in its own logical address space. Each can behave as if it has its own machine. A single logical address space can occupy disjoint pages in the physical address space. Thus, the addresses 100,000 and 200,000 in the programs. Logical address space need not be 100,000 bytes apart in physical memory. In fact, the physical address associated with logical address 100,000 may be larger than the physical address associated with logical address 200,000. The mapping from logical addresses to physical addresses is maintained cooperatively by the hardware and the operating system. It is, in almost all respects, beyond the compiler's purview. 7.2.2 Layout for data areas. For convenience, the compiler groups together the storage for values with the same lifetimes and visibility. It creates distinct data areas for them. The placement of these data areas depends on language rules about lifetimes and visibility of values. For example, the compiler can place procedural local automatic storage inside the procedure's activation record, precisely because the lifetimes of such variables matches the AR's lifetime. In contrast, it must place procedural local static storage where it will exist across invocations in the static region of memory. Figure 7.4 shows a typical compiler's view. Code static, keep stack, code static, keep stack, code static, keep stack. Code static, keep stack, virtual addresses. Physical address is large. Operating system's view. Hardware's view. Figure. Different views of the address space. If X is declared locally in procedure P and its value is not preserved across distinct invocations of P, then assign it to procedure local storage. If its value is preserved across invocations of P, then assign it to procedure local static storage. If X is declared as globally visible, then assign it to global storage. If X is allocated under program control, then assign it to the runtime heap. Figure. Assigning names to data areas. Set of rules for assigning a variable to a specific data area. Object-oriented languages follow different rules, but the problems are no more complex. Placing local automatic variables in the AR leads to efficient access. Since the code already needs the ARP and register, it can use ARP relative offsets to access these values with operations such as load I or load L. Frequent access to the AR will likely keep it in the data cache. The compiler places variables with either static lifetimes or global visibility in the data areas in the static region of memory. Access to these values takes slightly more work at runtime. The compiler must ensure that it has an address for the data area and a register. Values stored in the heap have lifetimes that the compiler cannot easily predict. A value can be placed in the heap by two distinct mechanisms. To establish the address of a static or global data area, the compiler typically loads a relocatable assembly language label. A primer on cache memories. One way that architects try to bridge the gap between processor speed and memory speed is through the use of cache memories. A cache is a small fast memory placed between the processor and main memory. The cache is divided into a series of equal-sized frames. Each frame has an address field called its tag that holds a main memory address. The hardware automatically maps memory locations to cache frames. The simplest mapping, used in a direct map cache, computes the cache address as the main memory address modulo the size of the cache. This partitions the memory into a linear set of blocks, each the size of a cache frame. A line is a memory block that maps to a frame. At any point in time, each cache frame holds a copy of the data from one of its blocks. Its tag field holds the address in memory where that data normally resides. On each read access to memory, the hardware checks to see if the requested word is already in its cache frame. If so, the requested bytes are returned to the processor. If not, the block currently in the frame is evicted and the requested block is brought into the cache. Some caches use more complex mappings. A set associative cache uses multiple frames for each cache line, typically 2 or 4 frames per line. A fully associative cache can place any block in any frame. Both these schemes use an associative search over the tags to determine if a block is in the cache. Associative schemes use a policy to determine which block to evict. Common schemes are random replacement and least recently used LRU replacement. In practice, the effective memory speed is determined by memory bandwidth, cache block length, the ratio of cache speed to memory speed, and the percentage of accesses that hit in the cache. From the compiler's perspective, the first three are fixed. Compiler-based efforts to improve memory performance focus on increasing the ratio of cache hits to cache misses called the hit ratio. Some architectures provide instructions that allow a program to give the cache hints as to when specific blocks should be brought into memory prefetch and when they are no longer needed flushed. The programmer can explicitly allocate storage from the heap. The compiler should not override that decision. The compiler can place a value on the heap when it detects that the value might outlive the procedure that created it. In either case, a value in the heap is represented by a full address rather than an offset from some base address. Assigning offsets in the case of local, static, and global data areas, the compiler must assign each name an offset inside the data area. Target ISIS constrain the placement of data items in memory. A typical set of constraints might specify that 32-bit integers and 32-bit floating point numbers begin on word 32-bit boundaries. That 64-bit integer and floating point data begin on double word 64-bit boundaries, and that string data begin on half-word 16-bit boundaries. We call these alignment rules. Some processors provide operations to implement procedure calls beyond a simple jump operation. Such support often adds further alignment constraints. For example, the ISA might dictate the format of the AR and the alignment of the start of each AR. The DEC VAX computers have a particularly elaborate call instruction. It stored registers and other parts of the processor state based on a call-specific bit mask that the compiler produced. For each data area, the compiler must compute a layout that assigns each variable in the data area its offset. That layout must comply with the ISIS alignment rules. The compiler may need to insert padding between some variables to obtain the proper alignments. To minimize wasted space, the compiler should order the variables into groups, from those with the most restrictive alignment rules to those with the least. For example, double word alignment is more restrictive than word alignment. The compiler then assigns offsets to the variables in the most restricted category, followed by the next most restricted class, and so on, until all variables have offsets. Since alignment rules almost always specify power of 2, the end of each category will naturally fit a restriction for the next category. Most assembly languages have directives to specify the alignment of the start of the data area, such as a double word boundary. Relative offsets and cache performance. The widespread use of cache memories in modern computer systems has subtle implications for the layout of variables in memory. If two values are used in proximity in the code, the compiler would like to ensure that they can reside in the cache at the same time. This can be accomplished in two ways. In the best situation, the two values would share a single cache block, which guarantees that the values are fetched from memory to the cache together. If they cannot share a cache block, the compiler would like to ensure that the two variables map to different cache lines. The compiler can achieve this by controlling the distance between their addresses. If we consider just two variables, controlling the distance between them seems manageable. When all the active variables are considered, however, the problem of optimal arrangement for a cache is NP-complete. Most variables have interactions with many other variables. This creates a web of relationships that the compiler may not be able to satisfy concurrently. If we consider a loop that uses several large arrays, the problem of arranging mutual non-interference becomes even worse. If the compiler can discover the relationship between the various array references in the loop, it can add padding between the arrays to increase the likelihood that the references hit different cache lines and thus do not interfere with each other. As we saw previously, the mapping of the program's logical address space to the hardware's physical address space need not preserve the distance between specific variables. Carrying this thought to its logical conclusion, the reader should ask how the compiler can ensure anything about relative offsets that are larger than the size of a virtual memory page. The processor's cache may use either virtual addresses or physical addresses in its tag fields. A virtually addressed cache preserves the spacing between values that the compiler creates. With such a cache, the compiler may be able to plan non-interference between large objects. With a physically addressed cache, the distance between two locations in different pages is determined by the page mapping unless cache size less than or equal to page size. Thus, the compiler's decisions about memory layout have little if any effect except within a single page. In this situation, the compiler should focus on getting objects that are referenced together into the same page and, if possible, the same cache line. Keeping values in registers. In a register-to-register memory model, the compiler tries to assign as many values as possible to virtual registers. In this approach, the compiler relies on the register allocator to map virtual registers in the IR to physical registers on the processor and to spill to memory any virtual register that it cannot keep in a physical register. If the compiler keeps a static value in a register, it must load the value before its first use in the procedure and store it back to memory before leaving the procedure, either at the procedure's exit or any call site within the procedure. Spill, when the register allocator cannot assign some virtual register to a physical register, it spills the value by storing it to RAM after each definition and loading it into a temporary register before each use. In most of the examples in this book, we follow a simple method for assigning virtual registers to values. Each value receives its own virtual register with a distinct subscript. This discipline exposes the largest set of values to subsequent analysis and optimization. It may in fact use too many names. See the digression, the impact of naming on page 248. However, this scheme has three principal advantages. It is simple. It can improve the results of analysis and optimization. It prevents the compiler writer from working processor-specific constraints into the code before optimization, thus enhancing portability. A strong register allocator can manage the namespace and tailor it precisely to the needs of the application and the resources available on the target processor. A value that the compiler can keep in a register is called an unambiguous value. A value that can have more than one name is called an ambiguous value. Ambiguity arises in several ways. Values stored in pointer-based variables are often ambiguous. Interactions between call by reference formal parameters and name scoping rules can make the formal parameters ambiguous. Many compilers treat array element values as ambiguous values because the compiler cannot tell if two references, such as and can ever refer to the same location. In general, the compiler cannot keep an ambiguous value in a register across either a definition or use of another ambiguous value. With careful analysis, the compiler can disambiguate some of these cases. Consider the sequence of assignments in the margin, assuming that both A and B are ambiguous. If A and B refer to the same location, then C gets the value 26. Otherwise, it receives M and 13. The compiler cannot keep A in a register across an assignment to another ambiguous variable unless it can prove that the set of locations to which the two names can refer are disjoint. This kind of comparative pairwise analysis is expensive, so compilers typically relegate ambiguous values to memory with a load before each use and a store after each definition. Analysis of ambiguity therefore focuses on proving that a given value is not ambiguous. The analysis might be cursory and local. For example, in C, any local variable whose address is never taken is unambiguous in the procedure where it is declared. More complex analyses build sets of possible names for each pointer variable. Any variable whose set has just one element is unambiguous. Unfortunately, analysis cannot resolve all ambiguities. Thus, the compiler must be prepared to handle ambiguous values cautiously and correctly. Language features can affect the compiler's ability to analyze ambiguity. For example, ANSI includes two keywords that directly communicate information about ambiguity. The restrict keyword informs the compiler that a pointer is unambiguous. It is often used when a procedure passes an address directly at a call site. The volatile keyword lets the programmer declare that the contents of a variable may change arbitrarily and without notice. It is used for hardware device registers and for variables that might be modified by interrupt service routines or other threads of control in an application. Unambiguous value. A value that can be accessed with just one name is an ambiguous. Ambiguous value. Any value that can be accessed by multiple names is ambiguous. AMN B13 CAB. Section review. The compiler must determine for each value computed in the program where it must be stored in memory or register, and in either case the specific location. It must assign to each value a location that is consistent with both its lifetime C section 6.3 and its addressability C section 6 risk. Thus, the compiler will group together values into data areas in which each value has the same storage class. Storage assignment provides the compiler with key opportunity to encode information into the IR for use by later passes. Specifically, the distinction between an ambiguous value and an unambiguous value can be hard to derive by analysis of the IR. If, however, the compiler assigns each unambiguous value its own virtual register for its entire lifetime, subsequent phases of the compiler can use a value storage location to determine whether or not a reference is ambiguous. This knowledge simplifies subsequent optimization. Void fee in A, B equal to AND. Review questions. 1. Sketch an algorithm that assigns offsets to a list of static variables in a single file from a C program. How does it order the variables? What alignment restrictions might your algorithm encounter? 2. Consider the short C fragment in the margin. It mentions 3 values, A, B, and B, which values are ambiguous, which are unambiguous. 7.3 arithmetic operators. Modern processors provide broad support for evaluating expressions. A typical RISC machine has a full complement of free address operations, including arithmetic operators, shifts, and Boolean operators. The free address form lets the compiler name the result of any operation and preserve it for later reuse. It also eliminates the major complication of the two address form, destructive operations. To generate code for a trivial expression, such as a B, the compiler first emits code to ensure that the values of A and B are in registers, say RA and RB. If A is stored in memory offset A in the current AR, the resulting code might be load R1, load R1, RA. If, however, the value of A is already in a register, the compiler can simply use that register in place of RA. The compiler follows a similar chain of decisions for B. Finally, it emits an instruction to perform the addition, such as add raw RBRT. If the expression is represented in a tree like IR, this process fits into a post-ordered tree walk. Figure 7.5a shows the code for a tree walk that generates code for simple expressions. It relies on two routines based on offset to hide some of the complexity. The base routine returns the name of a register holding the base address for an identifier. If needed, it emits code to get that address into a register. The offset routine has a similar function. It returns the name of a register holding the identifier's offset relative to the address returned by base. Expert note: ENT result T1 T2 switch type node. Case T1 extra left child node T2 extra right child node result next register. Emit node T1 T2 result break. Case ident T1 base node T2 offset node result next register. Emit load out T1 T2 result break. 7 BCB. Abstract syntax tree 4. ABXC case node result next register. Emit load eval node none result break return results. Load R1 load R1 R2 load B R3 load R3 R4 load C R5 load R5 R6 multi R4 R6 R7 sub R2 R7 R8. A. Tree walk code generator. C naive code. Figure 7.5 simple tree walk code generator for expressions. The same code handles. And from a code generation perspective, these operators are interchangeable, ignoring commutativity. Invoking the routine XBR from figure.a and the SC for ABXC shown in part B of the figure produces the result shown in part C of the figure. The example assumes that A, B, and C are not already in registers and that each reside in the current AR. Notice the similarity between the tree walk code generator and the ad hoc syntax directed translation scheme shown in figure 4.15. The tree walk makes more details explicit, including the handling of terminals and the evaluation order for subtrees. In the syntax directed translation scheme, the order of evaluation is controlled by the parser. Still, the two schemes produce roughly equivalent code, reducing demand for registers. Many issues affect the quality of the generated code. For example, the choice of storage locations has a direct impact, even for the simple expression. If A were in a global data area, the sequence of instructions needed to get A into a register might require an additional loading to obtain the base address and a register to hold that value for a brief time. Alternatively, if A were in a register, the two instructions used to load it into R could be omitted, and the compiler would use the name of the register holding it directly in the subinstruction. Keeping the value in a register avoids both the memory access and any address calculation. If A, B, and C were already in registers, the 7 instruction sequence could be shortened to a 2 instruction sequence. Code shape decisions encoded into the tree walk code generator have an effect on demand for registers. The naive code in the figure uses 8 registers plus RUB. It is tempting to assume that the register allocator, when it runs late in compilation, can reduce the number of registers to a minimum. For example, the register allocator could rewrite the code as shown in figure.a, which drops register use from 8 registers to 3 plus RUB. The maximum demand for registers occurs in the sequence that loads C and performs the multiply. A different code shape can reduce the demand for registers. The tree walk code generator loads A before it computes BXC, an artifact of the decision to use a left to right tree walk. Using a right to left tree walk would produce the code shown in figure 7, 6b, while the initial code uses the same number of registers as the code generated left to right. Register allocation reveals that the code actually needs one fewer registers, as shown in figure 7, 6c. Load out, multi sub. A. Example after allocation B evaluating BXC first C after register allocation. R1 RUB, R1 D R2 RUB, R2 R2 C R3 RUB, R3 R3 R2, R3 R2 R1, R2 R2. Load C R1 load R1 R2 load B R3 load R3 R4 multi R2 R4 R5 load. Figure. Rewriting ABXC to reduce demand for registers. Of course, right to left evaluation is not a general solution. For the expression AXBC, left to right evaluation produces a lower demand for registers. Some expressions such as a BCXC defy a simple static rule. The evaluation order that minimizes register demand is ABCXC. To choose an evaluation order that reduces demand for registers, the code generator must alternate between right and left children. It needs information about the detailed register needs of each subtree. As a rule, the compiler can minimize register use by evaluating first at each node the subtree that needs the most registers. The generated code must preserve the value of the first subtree that evaluates across the evaluation of the second subtree. Thus, handling the less demanding subtree first increases the demand for registers and the more demanding subtree by one register. This approach requires an initial pass over the code to compute demand for registers, followed by a pass that emits the actual code. This approach, analysis followed by transformation, applies in both code generation and optimization. 150. 7.3.2 accessing parameter values. The code generator in figure 7.5 implicitly assumes that a single access method works for all identifiers. Formal parameters may need different treatment. A call by value parameter passed in the AR can be handled as if it were a local variable. A call by reference parameter passed in the AR requires one additional indirection. Thus, for the call by reference parameter D, the compiler might generate load EDR load RUB, RR load RR to obtain DS value. The first two operations move the address of the parameter's value into R. The final operation moves the value itself into R3, generating load address immediate. A careful reader might notice that the code in figure 7.5 never generates ILOX load address immediate instruction, load EI. Instead, it generates a load immediate load E, followed by load address offset load L load R1 load R1 R2 instead of load IRUB R2. Throughout the book, the examples assume that it is preferable to generate this two operation sequence rather than a single operation. Three factors suggest this course. 1. The longer code sequence gives an explicit name to A if A is reused. In other contexts, that name can be reused. 2. The offset A may not fit in the immediate field of the load I. That determination is best made in the instruction selector. The two operation sequence leads to a clean functional decomposition in the code generator shown figure. The compiler can convert the two operation sequence into a single operation during optimization. If appropriate, for example, either A is not reused or it is cheaper to reload it. The best course, however, may be to defer the issue to instruction selection, thus isolating the machine-dependent constant length into a part of the compiler that is already highly machine-dependent. If the compiler writer wants to generate the load I earlier, two simple approaches work. The compiler writer can refactor the tree walk code generator in figure 7.5 and pull the logic hidden in base and offset into the case for ident. Alternatively, the compiler writer can have emit maintain a small instruction buffer, recognize the special case, and emit the load I. Using a small buffer makes this approach practical. See section 11.5. Many linkage conventions pass the first few parameters in registers. As written, the code in figure cannot handle a value that is permanently kept in a register. The necessary extensions, however, are easy to implement. Call by value parameters. The ident case must check if the value is already in a register. If so, it just assigns the register number to result. Otherwise, it uses the standard mechanisms to load the value from memory. Call by reference parameter. If the address resides in a register, the compiler simply loads the value into a register. If the address resides in the AR, it must load the address before it loads the value. Commutativity, associativity, and number systems. The compiler can often take advantage of algebraic properties of the operators. Addition and multiplication are commutative and associative, as are the Boolean operators. Thus, if the compiler sees a code fragment that computes a B and then computes BA with no intervening assignments to either A or B, it should recognize that they compute the same value. Similarly, if it sees the expressions A, B, C, and DAB, it should recognize that a B is a common subexpression. If it evaluates both expressions in strict left to right order, it will never recognize the common subexpression, since it will compute the second expression as DA and then DAB. The compiler should use commutativity and associativity to improve the quality of code that it generates. Reordering expressions can expose additional opportunities for many transformations. Due to limitations in precision, floating point numbers on a computer represent only a subset of the real numbers, one that does not preserve associativity. For this reason, compiler should not reorder floating point expressions unless the language definition specifically allows it. Consider the following example: computing A, B, C. We can assign floating point values to A, B, and C such that B, C, L, T, A, A, B, A, A, C, A, but A, B, C, A. In that case, the numerical result depends on the order of evaluation. Evaluating A, B, C produces a result identical to A, while evaluating B, C first and subtracting that quantity from A produces a result that is distinct from A. This problem arises from the approximate nature of floating point numbers. The mantissa is small relative to the range of the exponent. To add two numbers, the hardware must normalize them. If the difference in exponents is larger than the precision of the mantissa, the smaller number will be truncated to zero. The compiler cannot easily work its way around this issue, so it should, in general, avoid reordering float point computations. In either case, the code fits nicely into the tree walk framework. Note that the compiler cannot keep the value of a call by reference parameter in a register across an assignment unless the compiler can prove that the reference is unambiguous across all calls to the procedure. If the actual parameter is a local variable of the caller and its address is never taken, the corresponding formal is unambiguous. Function calls an expression. So far, we have assumed that all the operands in an expression are variables, constants, and temporary values produced by other subexpressions. Function calls also occur as operands in expressions. To evaluate a function call, the compiler simply generates the calling sequence needed to invoke the function and emits the code necessary to move the return value to a register. See section 7.9. The linkage convention limits the call's impact on the caller. The presence of a function call may restrict the compiler's ability to change an expression's evaluation order. The function may have side effects that modify the values of variables used in the expression. The compiler must respect the implied evaluation order of the source expression, at least with respect to the call. Without knowledge of the possible side effects of the call, the compiler cannot move references across the call. The compiler must assume the worst case of the function both modifies and uses every variable that it can access. The desire to improve on worst case assumptions, such as this one, has motivated much of the work in interprocedural analysis. See section 9.4, 7.3.4 other arithmetic operators. To handle other arithmetic operations, we can extend the tree walk model. The basic scheme remains the same. Get the operand into registers, perform the operation, and store the result. Operator precedence from the expression grammar ensures the correct evaluation order. Some operators require complex multi-operation sequences for their implementation, for example, exponentiation and trigonometric functions. These may be expanded inline or implemented with a call to a library routine supplied by the compiler or the operating system. 7.3.5 mixed type expressions.
I'm gonna read the papers now. There are two papers.
Extensional normalization and type-directed partial evaluation. For type lambda calculus with sums, Vincent Balla, PPS, Université Paris 7, Roberto de Cosmos, Université Paris 7, and Enria Rocancourt, Marcello Fiore, Computer Laboratory, University of Cambridge. Abstract: we present a notion of long normal term for the type lambda calculus with sums and prove, using Grothendieck logical relations, that every term is equivalent to one in normal form. Based on this development, we give the first type-directed partial evaluator that constructs normal forms of terms in this calculus. Categories and subject descriptors. F32. Logics and meanings of programs. Semantics of programming languages. Partial evaluation. Mathematical logic and formal languages. Mathematical logic, lambda calculus and related systems. D31. Programming languages. Formal definitions and theory semantics. General terms, languages, theory, algorithms. Keywords. Type lambda calculus, strong sums, Grothendieck logical relations, normalization, type-directed partial evaluation. Introduction. Some types and their associated case expressions are an essential feature of any programming language. Taking into account the full range of commuting conversions and performing program optimizations and partial evaluation in their presence is a difficult but important task. For example, consider the objective camel sum type AB sum left of a right of B, and the program match E with fun FGT, fun GGT, fun ZGT, fun XGT, left XGT to left XX match X with right XGT, T right XXX, left X1 greater than left Z right X2 greater than right GZ1. Some types satisfying this axiom are sometimes referred to as strong with or categorical sums. Left Y1 greater than FGY1, right Y2 greater than FY2. Amended version correcting an oversight in the treatment of the empty type pointed out to us by Frank Fenning. Research supported by an EPSRC Advanced Research Fellowship. Permission to make digital or hard copies of all or part of this work for personal or classroom use is granted without fee provided the copies are not made or distributed for profit or commercial advantage, and that copies bear this notice and the full citation on the first page. To copy otherwise, to republish, to post on servers, or to redistribute to lists requires prior specific permission and Popple 0, copyright TEX and. In this paper we consider some types in the
This is a problem with this kinds of papers using SpeechY. The formulas a lot of times are not parsed correctly. It's kind of annoying to. There's not that big of a deal, obviously. But sometimes it's harder to understand. So obviously I'm gonna go slower on this. Sure.
of type AGT, BGT, CGT, AGT, CGT, DE, some GT. This is a typical hard to read example of what automatically generated code looks like. Using commuting conversions, it can be transformed into the program. Fun F greater than fun G, greater than fun Z, greater than fun X, greater than match X with left X1 greater than match left Z with left Y1 greater than FGY1, right Y2 greater than FY2, right X2 greater than match right GZ with left Y1 greater than FGY1, right YGT FY, which can be then optimized into the program. Fun FGT, fun GGT, fun ZGT, fun XGT, match X with left XGT FGZ, right XGT FGZ. That by extensionality can be transformed into the more readable and efficient fun FGT, fun GGT, fun ZGT, fun XGT, FGZ. The commuting conversions associated to case expressions are derivable from the strong sum extensionality axiom, which identifies the programs. No known confluent and strongly normalizing reduction system for strong sums. Thus we consider below normalization fun FGT, fun GGT, and the program match E with fun FGT, fun G left X1 greater. Greater than left Z right X2 greater than right GZ1. Some types satisfying this axiom are sometimes referred to as strong with or categorical sums. In this paper we consider some types in the most basic foundational type theory for functional programming, the type lambda calculus with sums. In particular we tackle the problem of defining and computing normal forms in it so that for instance the passage from 1 to 2 can be done automatically. Besides the interest in the type lambda calculus with sums from the programming language viewpoint, there is also a type theoretic one, and the study of some types in this setting has proved challenging. See 17, 13, 16, 1. The theory of weak sums, either without the extensionality axiom C, or with the extensionality axiom restricted to the case TXC, is well understood. However, there is as yet, of type AGT, BGT, CGT, AGT, CGT, DE, some G, no known confluent and strongly normalizing reduction system for strong sums. Thus we consider below normalization within the whole calculus in the spirit of normalization by evaluation NBE and type-directed partial evaluation TDPE. NBE is a normalization technique introduced by Berger and Schwichtenberg for the simply type lambda calculus as an inverse to the evaluation function, mapping a semantic value into a syntactic one in normal form. Since then, NBE has been the subject of investigation in many domains: logic, type theory, category theory, partial evaluation. CEG 7. Partial evaluation is a program transformation technique used to specialize functions. TDPE is a partial evaluator for functional languages invented by Danby. It is based on the same principle as NBE. It constructs code of compiled programs, acting as a decompiler. An extension of NBE to the type lambda calculus with binary sums has been proposed by Altenkirch, Divier, Hoffman, and Scott 1. However, normalizing calculi with strong sums in the style of TDPE was an open problem, to which this paper offers a solution. For the type lambda calculus, Fiore 14 showed that we can extract the NBE algorithm as an intentional version of an extensional normalization result, stating that every term equals 1 in normal form. Here, in the context of the lambda calculus with sums, we start by following this analysis and present a notion of normal form with respect to which we establish an extensional normalization result. Afterwards, we proceed in a different direction and draw insight from the proof of this result to develop a partial evaluator for the type lambda calculus with binary sums that constructs normal forms. The extension to incorporate the empty type does not present much difficulty. The partial evaluator written in Objective Camel can be downloaded from the web. Organization of the paper. In section, we recall the syntax and semantics of the type lambda calculus with sums. In section 3, after recalling the construction of bicartesian closed categories of Grothendieck relations, we present a basic lemma that provides both guidelines for defining the notion of normal term given in section 4, and the proof skeleton for establishing the extensional normalization result of section 5. In section 6, we present the solution to normalization via TDPE for the simply type lambda calculus with binary sums. Concluding remarks are offered in section 7, 2 type lambda calculus with sums. We recall the syntax and categorical semantics of the simply type lambda calculus with empty and binary products and empty and binary sums. For details, see 20.2.1 syntax. The set of types has a countable set of base types and 2 type constants 1 and 0, the unit and empty type, and is closed under the formation of product function and sum type constructors. 4. Mali types are defined by the following grammar: base types unit type, t equal to 0, 1, t1 x t2 product types, tau iota 12 function types, 11 12 empty types sum types. The raw terms of the calculus are defined by the following gram: mar tx, tt, variables, unit, pairing, tt, ax tt, t1 12, 1 2 t 11.12 t8 t x1 t.
So this stuff I think is like basically the same there that I saw on the code there. It's just like I usually like, understanding this paper is usually harder than watching the videos. I think that the mathematical notation is a form of gatekeeping. It seems that they purposefully make it harder to understand. But yeah, I thought about like some time ago to spend a bunch of time trying to study more the symbols and stuff that you usually use on these papers, but it's still kind of confusing to understand. But it's basically saying showing the relationship there. So the product type would be the pair that I saw on the code there. The function is just the translation between one type to the other. The sum would be the union, and the empty type, I think, is the terminal. So there's the notion of terminal sets, which is a set where all the other sets go to. I think it's terminal sets or terminal sets, and then I'm not really sure if it's terminal set or terminal object. So you have basically the initial and the end. I think the initial is the empty one, and the terminal is the singleton, but I'm not 100% sure that's how it works. I think it makes sense to think about it this way because like the empty set would be like the void, so like 0, which is the set where everything comes from, and the terminal set would be like 1, which is the set where everything goes to, which is analogous to the way that the electromagnetic field works. So like the pressure mediation between the polarity seems to be located at the middle of the polarity, which is what creates the torus of the electromagnetic field. But realistically, the point of the pressure mediation exists in another realm, let's say, because it goes beyond the space. Space is just a projection of the pressure mediation. So maybe the product is different, and this is what the example is showing there.
One x2 d2 first projection, second projection abstraction application absurd first injection second injection discriminator, where x ranges over a countable set of variables. The unit pairing and abstraction are respectively the term constructors for the unit product and function types, whilst the projections and application are respectively the term destructors for the product and function types. The term constructors for sum types are given by the injections, whilst the absurd and discriminator are respectively the term destructors for empty and sum types. In particular, discriminator terms permit definitions by cases. The abstraction and discriminator are binding operators. X, tt binds the free occurrences of x and t, and t, x, t, x, t binds the free occurrences of x and ti I. The notions of free and bound variables are standard, and terms are identified up to alpha conversion. Notice that we have adopted a non-standard proof irrelevant version of absurd terms as L, rather than the standard one of the form. LT. This is important in the treatment of normal forms. As usual, we consider typing contexts as lists of type declarations for distinct variables, and say that a term t has type t in the context, if the judgment t is derivable from the rules of figure 1. Finally, we impose the standard notion of equality on terms, including the sum extensionality axiom, as detailed in figure, semantics. Bicartesian closed categories by CCs are categories with finite products, x, exponentials, and finite coproducts. The type lambda calculus with sums is the internal language of Biggs, and as
I think like the judgment is just like assignment or like a test of a proof or something like this. So the context is the stuff that I was seeing there, which is like it's kind of like a namespace, and the I think the t would be the variable and this symbol here would be the type. Yeah. So term is the t. So it's basically saying on this context, the variable has this, the variable t has this type here. And that's basically what the judgment is. Like a statement.
Such has sound and complete interpretations in them. With respect to an interpretation I of base types in a BICCS, we write IT for the interpretation of the type T induced by the bicartesian closed structure. That is, I, a base type, ITXT, it to type ITXT, XTXT, TH, N, YTN, T2, TK12, G, XT1, T2.
And this is the stuff I was saying before, where, as far as I know, you have like this, the line here that separates would be like the conclusion, let's say, and whatever is on top is like the statements. So it's like logical statements that allow you to nest proofs onto each other. It's like if 1 plus 1 equals 2, then you can say 2 plus 2 equals 4, for example. So like you stack up proofs. I'm not gonna spend time trying to like decipher every single thing here. I'm just gonna go over. And I'm not really sure if it's worth it, like because it's the thing that's about the Pareto distribution. So like I think it's usually better to just go over fast and until you find the places that matter, and then once you do that, then spend a bunch of time going in depth. And I do have to clarify these square brackets here. I've seen a bunch of times, and I don't understand what they mean very well. Maybe they talk about the beginning, and they don't show here. All here.
T L N G, XT1 T, yellow T wall, NCOT, X4 T1, X2, T2 T. Figure 1, typing rules. T equal to T, THT1 equal to T2, TT2 equal to T3, TTHT equal to T, TTT equal to T, TTT1 equal to T3, TFT, 1 THT equal to 1, T11 12 12, I equal to 1, 2 TFT, T1 times 12, TT1 T2 equal to T1, TITT1 T2 T, T1 XT2, X tone T, TTT1 tone to 7117 X and FVT, X T each T, equal to T11. Figure 2, equational theory of the type lambda calculus with sums, I0 equal to 0, I to T equal to T. This interpretation extends to context in the usual manner. 1x1 T1 Xn Tn equal to T1x X2T. We write IT for the morphism IT interpreting the judgment FTT syntactic BBICC. The syntactic BICC
Yeah, so this is what I mean. That's like it feels overly complicated. But basically, what I think they're saying is that in this context, based on if you have this judgment on this context, is like you're saying that you're gonna get the type here. So in this context, you get this type based on these judgments. It's basically saying that T is a type of this symbol here.
CC induced by the type theory has objects given by types and morphisms TT1 and 2 given by equivalence classes X, TO and TTT2, of derivable judgments under the equivalence identifying X, T1 TTT2 and X, T1T, T2 I have the judgment X, T1T equal to T, XX, T2 is derivable in the equational theory. Composition is by substitution. X T2 T30 times tone T T2 equal to X tone T T XC3, with identities given by X TXT, 3 bits of Grothendieck relations. The class of categorical models of the type.
And now I'm not really sure if it's supposed to go here. I'm just gonna continue though.
Typed lambda calculus with sums needed for establishing the extensional normalization result is that given by Bix of Grothendieck relation 16. These are categories defined over a site, a small category C with a Grothendieck topology K, equipped with an arity functors, CS into a BCCC. They consist of objects AR, where A is an object of S, and R is a Grothendieck relation of arity S, and have morphisms AR given by morphisms AA in S that preserve the relations. We recall the formal definitions. Definition 3.1.
I'm gonna ask ChatGPT, because this is another thing that is kind of weird about the definitions. I think it's the relationship between two different objects. That's weird.
A morphism is a fundamental concept in category theory that describes a structure-preserving map between two objects in a category. Here is a detailed breakdown of what a morphism is and its key properties. 1. Basic definition. In a category, a morphism is a mathematical abstraction representing a relationship or mapping between two objects. It can be thought of as a function or arrow that connects one object, the domain, to another object, the codomain. Morphisms are often denoted by arrows, such as FABF, a right arrow BFAB, where AAA and triple B are objects in the category, and FF is the morphism that maps AAA to triple B. 2. Types of morphisms. Endomorphism. A morphism where the domain and codomain are the same object, i.e., FF, a right arrow AFA. Isomorphism. A morphism that has an inverse, meaning there exists a morphism G-bag, B right arrow AG, BA such that gefickle toid X circ F equal to text equal toida, and equal toid BF circ G equal to text ID BFE equal.
Okay, so these I remember vaguely. Like G and F are like functions, and this symbol here is like the composition of two different functions. So this is saying G after F, which means you are gonna implement F on an object, and then you're gonna implement G. And that would be the same as implementing ID, which is the identity, which is the function that returns the thing itself. So it's basically saying that you have two objects, and then you have two arrows that connect the two objects, which are inverse functions of each other. So it means that, and then you on each object you're gonna have a function that returns itself, which is the ID. So it's like it's basically explaining this structure of the reverse functions.
F. A morphism is a fundamental concept in category theory that describes a structure-preserving map between two objects in a category. 2. Types of morphisms. Endomorphism. A morphism where the domain and codomain are the same object, i.e., FF, a right arrow AFA. Isomorphism. A morphism that has an inverse, meaning there exists a morphism G-bag, B right arrow AG, BA such that gefickle toid X circ F equal to text equal toida, and equal toid BF circ G equal to text ID BFE equal toid B, where IDX text IDX is the identity morphism on object 30th. Isomorphisms indicate the two objects are structurally the same. Monomorphism. A morphism that is injective, meaning it can be considered an embedding. If FABF, a right arrow BFAB is a monomorphism, it means that different elements in AAA map to different elements in BBB. Epimorphism. A morphism that is surjective, meaning it can be considered a projection. If FABF, a right arrow BFAB is an epimorphism, it indicates that every element in triple B has a preimage in AAA. 3. Composition of morphisms. Morphisms can
So this mapping here that it's talking about is the relationship between the objects on the SAT A and the objects on the SAT that encapsulates B. So like, and then they're connected through functions. So it's basically saying there's different types, different ways that the sets can relate to each other. And you have all these different names for the different ways.
can be composed, meaning if you have two morphisms, FABF, a right arrow BFAB, and GBCG, B right arrow CGBC, you can form a new morphism GFACG circ F, a right arrow CGFAC. The composition of morphisms is associative. If HCDH, C right arrow DHCD is another morphism, then HGF HGFH circ G circ F equal to H circ G circ F HGF HGF. 4. Identity morphism. For every object, AAA, in a category there exists an identity
So
morphism.
based on videos that I've seen, they say that it's not necessarily true that it's associative, which means that the order in which you do the operations don't matter. Is that they do it this way because it simplifies a lot how to understand the stuff. But there must be situations where there is a difference. So it would be more like a matrix multiplication, where depending on the order, it affects how it works. But to simplify, you can do it. You can assume that is associative.
Ida, a right arrow Ida. That acts as a neutral element under composition. It satisfies the properties I def equal tof text I circ f equal to phi def equal tof for any morphism f abf a right row bf abby get equal tog circ text today equal to get equal tog for any morphism g bag b right row ag ba. 5. Preserving structure. Morphisms are defined to preserve the structure of objects in a category. For example, in the category of sets, morphisms are functions that map elements of one set to another. In the category of groups, morphisms are group homomorphisms that preserve the group operation. In the category of topological spaces, morphisms are continuous functions that preserve the topological structure. 6. Examples of morphisms. Set category. In the category of sets, morphisms are functions. For instance, if equal to 1, 2a equal to 1, 2 equal to 1, 2, and equal to 3, 4, 5b equal to 3, 4, 5 equal to 3, 4, 5. A morphism FABF, a right arrow BFAB, could be defined as F1 equal to 3 Fahrenheit 1 equal to 3 Fahrenheit 1 equal to 3, F2 equal to 4 Fahrenheit 2 equal to 4 Fahrenheit 2 equal to 4. Vector spaces. In the category of vector spaces, morphisms are linear transformations. If VV and WW are vector spaces, a morphism T VWT V right arrow WTVW must preserve vector addition and scalar multiplication. Topological spaces. In the category of topological spaces, morphisms are continuous functions which preserve the open sets of the topology. Summary. A morphism is a structure-preserving map between objects in a category. It provides a way to express relationships between different mathematical structures while respecting their intrinsic properties. Morphisms can be composed, possess identity morphisms, and can be classified into various types based on their properties, e.g., isomorphisms, monomorphisms, epimorphisms. This abstraction is crucial in category theory, allowing for a unified way to study different mathematical concepts.
I think I understand what it means.
Given a small category C, a basis for a Grothendieck topology K on C is given by associating to each object A of C a collection Ka of covers of a family of morphisms in C with codomain A, satisfying the following conditions. Identity. For every CKA contains the family consisting of the identity morphism on A. Stability. For every II Leonka A and morphism BA, there exists a family BIB JK B such that every OB A factors through some II for every JJ there exists II and YJ B such that transitivity. For every IAI Leonka A and for every Yigel Ek II the family Yigel JK A. A small category together with a Grothendieck tautology on it is called a site. Definition 3.2. For a site CK and a functors, CSACK Grothendieck relation R of arity S over A and E S is a family R C S C A C E C with the following two properties. Monotonicity. For every C and C and every X S is C A and S, if X equal to RC then X O is equal to RC. Local character. For every cover ICCL C and for every X is C A and S, if XO is IRCI for all II, then X equal to RC. Definition 3.3. For a site CK and a functor CS, the category of Grothendieck relations GCK, S is defined as follows. Objects are pairs AR consisting of an object A and S and AC. K Grothendieck relation R of arity S over A. Morphisms AR are morphisms F, AA and S such that for all objects C and C, and morphisms X, S is C A and RC. The composite Fox is in RC. We have the following important results. See 16 for details. Proposition 3.4. For a site CK and a functors, CS into a bicartesian closed category. The category of Grothendieck relations GCKS is bicartesian closed, and the forgetful functor GCKSS preserves the bicartesian closed structure. The fundamental lemma of Grothendieck logical relations follows as a corollary. Lemma 3.5 fundamental lemma. For a family of Grothendieck relations I0, re E and GCKSCS indexed by base types. Let IT R resp. 2. R and R be the family of Grothendieck relations indexed by types resp. Context induced by the bicartesian closed structure of GCKS. Then the interpretation of terms IT, R IT are morphisms I, R R IT, R in GCKS. 3.1 basic lemma. Following the analysis of 14, we give a basic lemma that provides the proof skeleton for both the definability result of 16 and the extensional normalization result theorem 5.1 of this paper. Lemma 3.6 basic lemma. Consider a C to CK, a functor S, CS into a BIC, and an interpretation I of base types in S, let I to land it, or be two families of Grothendieck relations in GCK, is indexed by type such that L1 equal to 1, locks close, lot C level, U11 equal to T, uvu UT, luug T for a family of Grothendieck relations 0 re and GCK S is indexed by base types, let IT, R be the family of Grothendieck relations indexed by types induced by the bicartesian closed structure of GCK S. If Q for all base types then, 1, CRCU for all types T, and thus, 2, for all terms T, TF equal to XT, XN, TN and tuples. As C and LC 1 less than or equal to less than or equal to NCEC, we have that it, TN to CIT is in UT. The first part of the lemma follows by induction on types using the closure properties of the hypothesis and the functoriality of the categorical type constructors. The second part is a consequence of the first and the fundamental lemma. For normal forms, we present a notion of net long-set normal form for the type lambda calculus with sums. The overall definition, which is given in figure 3, depends on four mutual inductively defined entailment systems: pure neutral terms, min-neutral terms, no pure normal terms, and normal terms. The pure neutral terms are essentially given as in the type lambda calculus, whilst the neutral terms are obtained from these by closing under discriminators. The pure normal terms are essentially given as in the type lambda calculus with the addition of the sum injections, and normal terms are obtained by closing under discriminators with respect to pure neutral terms. The unique neutral and normal term in an inconsistent context viz. A context in which the judgment 10, 0 is derivable if type T is lieutenant. The definition of normal forms has been designed guided by that of 1, of which the ones here are syntactic counterparts, and by making sure that the interpretations of neutral and normal terms provide Grothendieck relations satisfying the hypothesis of the basic lemma. See section 3. Note that there are syntactically different but semantically equivalent normal forms like the following ones. And AG 00102H 00304DX0 AGX x1.11 x2.8 HX 1.12 y2.11 AG 00002.88 00304 which 00004 which differ only in the order in which the case analysis is performed. This situation is formalized by the relation in the definition below, on which the side conditions B and C of figure 3, allowing the closure under discriminators of normal terms depend. Definition 4.1. We let be the least congruence between well-typed terms of the same type such that 8m x.8m1 approximately equal to 8m1 x1.8m xn1 yn x2.8m xn2 yn r8m yn x8m1 x1n1 x2n2 8m1 x1.8m yn xn1 x2.6m yn xn2 xt I'm xttmm t1 xt2 m ti equal to 1 2 ehem mt1 at t10 t1 tfmm nt dm t tem t I inconsistent tfm ltt timo mt1 t2 g 11 milhões ti igual a 1.2 mm x1.m1 x2 m2t tmm0 tem0 e a base type TNET I equal to 1 2 T and 1 trillion N1 N2 T1 XT2 TNET tells N 7172 I equal to 1 2 10 nit textnet T x 10 TC is not typable in context for all C guards XTN Gamma iota alpha lambda Toyota nu Toyota tau I inconsistent 10 li T mm T1 T2 X11 N1 I equal to 1 2 M X1 N1 X2 N2 TMC for all C U1 2 guards N1 and 2 whenever NT I equal to 1 2 A MM is typable in context UU1 2 guards NA if N equal to 8M X1 N1 X2 N2 def guards and 0 otherwise. Figure 3 neutral and normal terms. The context is assumed consistent unless stated otherwise. Gamma epsilon alpha nu T minus 8 M X N Y N equal to N 10 1 inconsistent. If desired unique representatives for normal terms can be chosen. Indeed, in one, this is done by considering a generalized form of discriminator construct, allowing simultaneous case analysis. Alternatively, one could proceed by both fixing a canonical notation for binders and a linear order on pure neutral terms to be respected in nested discriminators. This, we believe, yields unique normal forms. For instance, adopting the canonical notation for binders provided by de Bruijn levels. The normal form for the terms 3 and 4 under the linear order in which Lo2 precedes L1 L2 is manner 00304 lambda 20 8 Lo L2 L3.1 L3 D L1 L2 L4.12 4.11. Examples. We conclude the section with examples of terms and their normal forms that will help to elucidate the notion. To grasp the role of the side conditions in Figure 3, note that condition A fixes the relative position of abstractions and discriminators. Condition B forbids dead branches, that is, when the same case analysis is performed more than once, and hence becomes redundant. And condition C forbids the two branches of a discriminator to be the same, as in such case the discriminator is redundant. Example 4.2. 1. The identity term x 0.x of type 00 is a normal term. 2. The identity term xx 0102x of type 0102 0102 is not a normal term. Its normal form is x 102.8x, x 1.11, x1, x 2.10, x 010, x of type 010, 102, equivalent normal terms, x 0102, x 00, delta g, x 1.82, x 141, x1, 11x, the curried identity term xx 0102aa, 010, xy, of type 0102, 0012, 0102, 10, has as unique normal form the term xx 0102, 8x, x1, a 00.8y. y2, 11x1, 12y2, x2, I00, 8y yon, 12x2, 11 yon, 2, 12x2. Example 4.3. Let A equal to 1111, B equal to 1112, C equal to 1211, and D equal to 1212 of type 1111. 1. The term x 102.88x x1a x2d 1.121 y2.1192 is not a normal term because x01, 02 mo8x x1a x2d 1111. Its normal form is the term 2. The term AF 0 x 012.8x x1c x2b 0102 xx 0.1 gram 000.a0 8gy x12b x2.8 gy. Normal term because condition A is not satisfied. Is not. Its normal form is the term AF 00102 x08 fx91 ag 00012 8gx y2 ag0 21.a 0.8 gy x1.a x2c 22a x1 8 gy x2 x21a 0.8 gy x1b x2c 22a 0.8 gy x1b x2d gy x112 x2 Psychosiocto. Lvio x 6 2.12 92.11 does not satisfy condition B and so is not a normal term. Its normal forms are AF 00102 00304 011 0506 and 8FA 00102 AH 00304X 22C x1.8 and 22C x1 00102 00304 11 0506 8FAG 0002.1 hours 00304X0 8HX Y1.8GX as a direct consequent one. As a direct result that for every term T there exists a normal term N such that it equal to IN, IT, and S. The syntactic result of theorem 5 x 21a 22c4 the term AF 00 lambda x 00.8x x1 x1 x2 but is not normal as F000 x00 x10 x10 because the context is inconsistent. The equivalent term AF 00.x00.5x x1.10 x2.10 is not normal either because condition C is not satisfied. The normal form of these two terms is AF 000.x 00.10. Example 4.4. The normal form of the term is AF 010.x 01 2.19 0201y 0 8x x1.li x2. AF 010.x 01 plus 2.1 8x x102 01001 x2.190. 5. Extensional normalization. Following 14, we establish the following extensional normalization result. Theorem 5.1 Extensional normalization. For every term of the type lambda calculus with sumst, there exists a normal term nt such that t equal to n is provable in the equational theory of the calculus. The proof is along the following lines. We define an appropriate syntactic site ck together with an arity functor I cs into a bicc canonically induced by a stable interpretation I of base types. See section 5.1. We establish that the interpretation of neutral and normal terms define Grothendieck relations in GCKI satisfying the
I ask what the fuck is graph and whatever. Yeah, I don't understand what he's saying there. I'm not gonna spend time trying to understand now. Just gonna look into the terms.
Alexander Grothendieck was a highly influential French mathematician, widely regarded as one of the most significant mathematicians of the 20th century. He made profound contributions to several areas of mathematics, particularly algebraic geometry, category theory, and homological algebra. Here are some key points about Grothendieck and his work. 1. Background. Grothendieck was born on March 28, 1928, in Berlin, Germany, to a Jewish father and a German mother. His family fled to France during World War II to escape the Nazi regime. He was educated in France and developed a strong interest in mathematics, ultimately studying at the University of Montpellier. 2. Contributions to algebraic geometry. Grothendieck revolutionized algebraic geometry by introducing a new framework that unified many disparate results and concepts. He developed the theory of schemes, which generalizes the notion of algebraic varieties and allows mathematicians to study geometric objects using the language of commutative algebra. His work on schemes laid the groundwork for much of modern algebraic geometry, enabling deep connections with other areas of mathematics, including number theory and topology. 3. Category theory. Grothendieck was instrumental in bringing category theory into mainstream mathematics. He emphasized the importance of categorical thinking in various branches of mathematics. He introduced concepts such as functors, natural transformations, and limits, and he emphasized the role of universal properties in mathematics. His work also included the development of the Grothendieck topology, a generalization of the notion of a topological space that plays a crucial role in modern algebraic geometry. 4. Homological algebra. Grothendieck made significant advancements in homological algebra, particularly through his work on derived categories and the theory of sheaves. He introduced the notion of abelian categories and established the foundations for modern homological methods, including spectral sequences and the Grothendieck duality. 5. Grothendieck's work on the Langlands program. Grothendieck contributed to the Langlands program, a set of conjectures and theorems connecting number theory and representation theory, through his insights in algebraic geometry. 6. Philosophical approach to mathematics. Grothendieck had a distinctive philosophical approach to mathematics, emphasizing intuition and the underlying structures of mathematical objects. He often expressed concerns about the societal impact of mathematics and its applications, especially in the context of war and technology. 7. Later life and retreat from mathematics. After the 1980s, Grothendieck gradually withdrew from the mathematical community, becoming reclusive. He lived in the south of France, where he focused on personal projects and philosophical writings. He passed away on November 13, 2014, in a small village in France. 8. Legacy. Grothendieck's ideas have had a lasting impact on modern mathematics. His work has influenced generations of mathematicians and has led to the development of many areas of research. He received numerous awards and honors for his contributions, including the Fields Medal in 1966, though he famously declined to attend the International Congress of Mathematicians to receive it. Key concepts associated with Grothendieck. Schemes, a fundamental concept in modern algebraic geometry. Sheaves, a tool for systematically tracking local data attached to the open sets of a topological space. Grothendieck topologies, generalizations of the concept of a topology, important in the study of sheaves and cohomology. Derived categories, a way of formalizing the notion of homological algebra to study properties of complexes of objects. Grothendieck universes, a set theoretic framework he developed to handle large categories and foundations in category theory. Grothendieck's profound ideas continue to resonate throughout mathematics, providing powerful tools and frameworks for understanding complex mathematical structures and relationships. Hypothesis of the basic lemma. See section 5.2. Mom T112, Tx T1 equal to 4x equal to 112 millions I equal to 1 2. Inconsistent. 8hx, y1.8 gx. As a direct consequent one. As a direct result that for every term t there exists a normal term n such that it equal to in, it, and s. The syntactic result of theorem 5.1 follows from the semantic one by embedding the syntactic by c, induced by the type theory into a Bibichian which the sums become. 5.1. The syntactic site and its arity functor. The syntactic site. Following 16 in the light of 1, we will use a site of constrained contexts. E. The intuition is that we consider the context under the constraints. E. Definition 5.2. Constrained contexts are defined by the follow. Ing rules gamma epsilon.xt, x equal to xx, 21a, 22c4. The term af 00 lambda x, 00. The syntactic site. Following 16 in the light of 1, we will use a site of constrained contexts. E. The intuition is that we consider the context under the constraints. E. Definition 5.2. Constrained contexts are defined by the follow. Ing rules gamma epsilon.xt, x equal to xx, 21a, 22c4. The term af 00 lambda x, 00.8x, x1, x1, x2, but is not normal. 2. Where x dom are. Definition 5.3. The category C has objects given by constrained contexts and morphisms e.e. given by injective renamings p dom dom that preserve typing, that is if xt, then p x ter n constraints that is if equal to 3 euros, then tp equal to p 3 euros. Definition 5.4. The family of covers ke of a constrained context is defined by the following rules. 0 ke inconsistent, idem r ek. Pj jejup, ete, pj jeju popi equal to 1 2, where for I equal to 1 2, the constrained contexts are of the form x equal to 1 2 trillions, and the renamings p1 are the inclusions ami. Proposition 5.5. The pair ck is a site, the arity functor. We restrict attention to stable interpretations of types, i.e. interpretations I of base types in a BIC such that for all pair of types tt1 and tt2, the coproduct tt1 2 is stable under pullbacks. For a stable interpretation, we define the semantic interpretation of the constrained context E as a subobject of the semantic interpretation of the context. Definition 5.6. With respect to a stable interpretation Y of base types in a BICs, we associate to every constrained context E its interpretation IE, given by the domain of a monomorphism MRE, IR, inductively defined as follows. M010, 11 is defined as ID1. MRXT, x equal to XET second is defined as merexit. MRXT 111x equal to 1 2. XT4x equal to 11 12 trillions. Greater than IT is defined as Mr. Pi chi where the following square. T, XTX equal to 1 T2T, Q, Pi it, Merzi, gamma, T11 12. Proposi Cyan 5.8. Let one be a stable is a pullback, IT to 1 2, Li 1, by stability the family, IT, she equal to T1 T2T, is a coproduct, and for every pi e minus 1 2, to equal to x1 T1 xn Tn T1 equal to retin Tr, we have an equalizer diagram, Tt is ein, Merzi greater than I it, Gt, R, isosin. The definition of the arity functor induced by a stable interpretation follows. Definition 5.7. With respect to a stable interpretation I of base types in a bi-CCS, the arity functor I, CS is defined as follows. On objects I defite. On morphisms for PE we define IP as the unique, map I such that 7 gamma epsilon, IP, Mrs. R equal to x dom R fx. 1 pip xx dom, I equal to x dom R ixation result, extensional normally. For a stable interpretation I of base types in a bit triple CS the definitions. Equal to im, tom equal to tm m t, in, tom equal to n and t, Mr. equal to, nu gamma epsilon. Respectively identify the sets of neutral and normal morphisms in cis IE, IT. The proof of the theorem relies on the next two lemmas, whose proofs embody the algorithm. Proposi Cyan 5.8. Let one be a stable interpretation of base types in a BIC. For all types T, it, M, and IT, N are Grothendieck relations in GCKI. Theorem 5.9. The Grothendieck relations of neutral and normal morphisms satisfy the following closure properties. M equal to 1 and 1 equal to T. Mot mov mt no vngc nox mono Mr. no vnc no t mo n no T. And me no 0 a base type is a pullback, IT to 1 2. The proof of the theorem relies on the next two lemmas, whose proofs embody the algorithmic idea underlying the normalization program of section 6, lemma 5.10. 1. For every neutral term, there exist neutral terms fm1 t1 and, such that pi may equal to m1 t1 I equal to 1 2, m1 xt2, m2 t2, 2. For every neutral term m and m tone t and normal term tn t1, there exists a neutral term m and m t such that min m t lemma 5.11. 1. For every term ct derivable accord, ing to the following rules. Tn t10 eti consistent, m t112 txt I equal to 1 2. M x1 c1 x2 c2 t10 li t I consistent, inconsistent. There exists a normal term nt such that c equal to n t2. For every pair of normal terms there exists a normal term n1 n2 and t1 xt2. Noon ti equal to 1 2 n and t1 xt2 such that 3. For every normal term n t1 I equal to 1 2, there exists a normal term n t1 t2 such that 1 n equal to n t1 t2. 4. For every normal term x tone non t there exists a normal term nt1 t such that x t1 n1 equal to n iota tau. Since we're equal to xt xn tn we have that the projection x less than or equal to less than or equal ton is a neutral morphism it in Mr. R, where ar equal to x1 equal to x xn equal toxin. It follows from theorem 5.9 and the basic lemma that the interpretation it equal to t to c11 xn tn of the term t is a normal morphism t in an R. Thus we have the following corollary. Corollary 5.12. Let I be a stable interpretation of base types in a bit CS. For every term t x there exists a normal term n, such that I st x equal to f n t, a t and f. Theorem 5.2 is obtained from this corollary by producing a BIC embedding tt of the syntactic BBIC into a BBIC state, mapping sums to stable sums, and considering the canonical interpretation of types in T. 6 type directed partial evaluation with binary sums. We show how to build a normalization algorithm based on type directed partial evaluation that puts terms in the normal form of section 4. In fact, we use a version of TDPE written for the language objective camel C2, slightly modified to allow the use of certain powerful control operators. An interesting point of this work is that the optimizations we introduce will be usable in some other cases of partial evaluation. Here, however, we are only concerned in normalizing functional programs corresponding to terms in the type lambda calculus with binary sums with respect to the equational theory of the calculus. In particular, note that the normalization of a program may have a different observational semantics within the programming language that is than the original program. As for instance, the evaluation order may not be preserved. We recall the basic original TDPE. We recall the basic elements of the original TDPE algorithm. For details, see 5.6. NBE is based on an n expansion of the term using a two-level language, which in our case is defined as follows. T equal to s is static terms. ds equal to x. d equal to dynamic terms. Pair tone t2 pione t p2 t. ax t t1 t2 11 t2 t8 t x1 t1 x2 t2. Pair t1 t2 1 t2 t. ax t tone t2 1 t2 t8 t x1 t1 x2 t2, where x resp. X ranges over a countable set of static resp dynamic variables. The set terms are said to be static, and the dat terms to be dynamic. In implementations, dynamic terms are often represented by data structures, whereas static terms are values of the language itself. The TDPE algorithm without let insertion is presented in Figure 4. It inductively defines two functions for each type. One written is called reify, and the other one written is called reflect. The functions are basically two-level net expansions. To normalize a static value v of type t, first apply the function to v and then reduce the static part, obtaining a fully dynamic term in normal form. The reduction of static parts is performed automatically by the abstract machine of the programming language. The control operators shift and reset are used to place 8 in the right place in the final result. Shift and reset. We briefly explain the way in which shift and reset work with an example. For details, see 8.9. The operator reset is used to delimit a context of evaluation, and shift abstracts this context in a function. Thus the term 1 reset 2 plus shift c, 3 plus c4 c5, reduces to 13 plus 2 4 2 5. Indeed, the operator reset delimits the context 2 plus, which is abstracted into the function c. The values 4 and 5 are successively inserted in this context, and the resulting expression is evaluated. 6.2 Producing normal terms. The original TDP algorithm without let insertion produces terms following the inference system of Figure 3, without taking into account the side. Conditions A, B, C therein. For example, the evaluation of the term a z ax af8 fxx1 a z af z of type 000000102 yields the term az.x.af a suggests satisfying condition x1, which does not satisfy condition A since fz does not contain the variable y. In the following, we propose 3 modifications of TDPE to take the conditions A, B, C into account. 6.2.1 Remove dead branches. To ensure the condition B, we will use the following derivable equations. 8tx, 8tx1, t1x2, t2y, to equal to 8tx, tone xx1y, 2, 8tx2y, tx1, t1x2, t2 equal to 8tx2y, t2yx2. To apply these transformations, notice that the residual program is an abstract syntax tree built in depth-first manner from left to right, the evaluation being done in call by value. The idea consists in maintaining a global table accounting for the conditional branches in the path from the root of the residual program to the current point of construction. This table associates a flag L or R and a variable, VVE base type, M10 millions, 101x02M, 101 millions. Let x be a fresh variable in ax.reset v1x pair v22v, 8v x1.111 test1, x2.12x to1, 8v x1272 x variables. In shift C, M, x1.reset C11 degree 11, reset C. Figure 4, type directed partial evaluation without let insertion, to an expression in the following way, 10102 millions equal to if M is globally associated to L2 modulo then 112. Else if M is globally associated to RZ modulo, then 12122. Else shift C, let x and x2 be fresh variables. In, associate M to LX1 while computing. 11 reset 1x1, associate M to RX2, while computing 12 equal to reset 12 12x2. N2, note that the test of global association is done modulo. This is explained in the next section. This optimization, associated with let insertion and other memoization techniques, has been used for building a fully lazy partial evaluator from TDPE C3. 6.2.2 Forbid redundant discriminators. To enforce the condition.
I'm gonna see, I don't understand very well what exactly is saying here. I just very superficially some concepts I understand, but I think what I'm gonna do is try to find actual implementations, because reading the code is gonna be, usually it is like this, like reading the code is a lot easier to understand than reading the papers because of all these symbols here. So that's why I asked ChatGPT. So I'm probably gonna search for repositories or actual code. I'm gonna use Perplexity probably to search for implementations of this algorithm. But I think that what they're talking about is like the proof. So they're going over the logic and yeah, the proof basically that this works. which is a way to derive types, I think.
C. We write a test of membership of free variables and implement a test of the congruence of two normal terms. There are different ways in which to implement this latter test. One method is to define, in a mutually recursive fashion, three tests, and that respectively test the equivalence between pure neutral terms, pure normal terms, and normal terms along the following lines. The test is done by structural recursion, using the test in the case of applications. The test is done by structural recursion, using the test in the case of abstractions. The test NN inspects the set of paths P given by all possible branchings and discriminators containing the guards of N, and collects the sequence of guards together with the end pure normal form NP. For each of these paths P, it proceeds according to the following subtest. If N is a pure normal term, then check whether NP no N otherwise. For N of the form 5M, X, N1, YN, there are three possibilities. If M is in the path P up to and the path branches left resp, right, the subtest is repeated for N1 resp, N12 instead of N. However, if M is not in the path P up to mo, the subtest is repeated for both N and N12 instead of N, succeeding if both of these subtests do. Note that condition C does not need to be checked recursively within the branches of the discriminator, since as TDPE builds the normal form in depth first manner, it is known that each branch satisfies it. 6.2.3. Fix the relative positions of abstractions and discriminators. To obtain terms in normal form, we must also check the condition A concerning the guards of abstractions. For that, let us look at the example in 5.
This is very interesting though, because basically what I was saying, like, is the connection between the type theory and the compilation process. So I think it's gonna be a very good way to, hopefully, if I find a code, it's gonna be a lot better to try to understand. Because basically, he's mentioning abstract syntax tree. So imagine what this is saying is they're going to use these notions of the categories and type theory to build the grammar that is going to help, or is going to allow you to build the abstract syntax tree based on this relationship between types and functors and functions. But I don't understand the symbols and most of the stuff that they are talking about here.
Introduce the FZ above I. However, a shift always returns to the preceding reset. Thus, it would be necessary to be able to name each reset and to choose the best one at the time of introducing the 8. This is what the control operators cupto, set, introduced in 19 allow us to do. Set and cupto. The control operators set and cupto are very powerful and generalize exceptions and continuations. Here we give the idea of how they work on an example. For details, see 1918. The operators set, cupto rely on the concept of prompt that allows marking the occurrences of set. New prompts can be created upon request. For two prompts P1 and P2, one can write an expression like the following: 1 plus set P1 and 2 plus set P2 and 3 plus cupto P1 as C and 4 C5, which evaluates to 1 4 2 3 5. Application to TDPE. To use set cupto to address the problem of fixing the relative position of abstractions and discriminators, we must create a new prompt with each created dynamic A. Further, we maintain a global list associating to each prompt a set of variables. To introduce a new 8, we look for all the free variables of its condition, and look in this list for the last prompt introduced to which one of these variables is associated. Since the term is built in depth first manner, and from left to right, one obtains a closed term, we thus modify the algorithm of TDPE in the following way. Let x be a fresh variable and p be a new prompt in x. Set pin v1 x fifth 110 millions equal to let m be the best prompt for m. In cup to mass c and let x and x be fresh variables. N1 set m and c11 1 text 1. N2 set m x 1.1. N2 set algorithm is presented in figure 5. 2. 1. We show the application of the optimized partial evaluator to the example of the introduction. Hashtag let example fgzx equal to matches match x with left xl greater than left z, right x2 greater than right gz, left while fg on right y2 greater than fy2. Val example ab greater than c greater than a greater than c d e sum greater than b equal to less than fun greater than. To use a type-directed partial evaluator, one has to pass to the evaluator a representation of the type of the term to be evaluated. There are different approaches to representing types. Here we use the approach pioneered by Felinsky, who represents types via combinator, so that a greater than c greater than a greater than c d e sum greater than b becomes base greater than base greater than sum base.
I think that the implementation of these things is not very, like, it's not hard to understand. It's gonna be something similar to the code there that I saw, because they're basically saying, like, this is gonna be implemented when you're traveling on the abstract syntax tree to derive meaning from, like, the sentences. So after you have the tokens, you generate the abstract syntax tree using a recursive parser, I think. And they're saying that they're going to use these types, the relationship between types, to derive other types based on the order of recursion, which they're saying is going to be that first from left to right. So imagine that on the actual code, it's going to be like just matching the patterns according to the way that you traverse the tokens. And using these rules from type theory and category theory to derive what other types are going to be based on the types you have on the language. But the problem is that it doesn't, there's still like stuff that is kind of hard to understand, because I think it's more abstract, that goes beyond the implementation of the thing on the language. But I think it's gonna be like a one step further to understand. Like, once you understand how to, it is like a good thing, I think, to, so like the first focus is gonna be to understand how to implement this on the actual compiler. So find the code and then implement. Then after I understand this, it's going to become more clear on the relationship, the more abstract relationship of what it means to implement this stuff. But it might be easier than what I'm thinking about, actually. Yeah, I think that the actual thing is easier, but what it implies is a lot harder to understand. And probably going to be a lot harder as well to find content, if there is content on this.
Base greater than base, which we abbreviate below as combinator type. The application of the partial evaluator based on shift reset yields. Hashtag TDPSR combinator type example. Shift reset dot ans equal to fun v0 v1 v2 v3 greater than match v3 with left v4 v0 v1 v2 right v4 greater than v0 v1 v2. Whilst the partial evaluator based on cupto produces the desired result. Hashtag TDP cupto combinator type example. Normal equal to fun FGZ x greater than FGZ. 2. We now test the partial evaluator on an example suggested to us by Felinsky. For every endo function f on a two-element set, the identity f3 equal to f holds. We give a proof of this fact in the equational theory of the type lambda calculus with sums by establishing the identity AF1111x11 equal to AF1111 in the equational theory using the partial evaluator. Defining hashtag let ffx equal to ffx val f greater than a greater than a greater than a equal to less than fun greater than and hashtag let bool sum unit. We want that the normalization of ff of type bool greater than bool is the normal form of the identity. Normalizing ff by the TDPE with shift reset gives the following uninformative result. Hashtag TDPS or bool greater than bool ff. Shift reset dot ans equal to fun v0 v1 greater than match v1 with left v2 greater than match v0 left with left v10 greater than match v0 left with left v14 greater than match v0 left with left v16 greater than left right v16 greater than right right v14 greater than match v0 right with left v15 greater than left right v15 greater than right right v10 greater than match v0 right with left v11 greater than match v0 left with left v13 greater than left right v13 greater than right right v11 greater than match v0 right with left v12 greater than left right v12 greater than right v2 greater than match v0 right with left v3 greater than match v0 left with left v7 greater than match v0 left with left v9 greater than left right v9 greater than right right v7 match v0 right with right v3 greater than left v8 greater than left right v8 greater than right live v equal to 1 volt low fifth 1x2 v equal to m 1710 millions 101 times 0 2 m equal to 10,102 millions fifth let x be a fresh variable and p a new prompt in ax set p in ns v deca times pair v ivan dio v octo v x deca ns xenas x diacosia deca dioxtio m x ns m ns times pair m ns dio m. If m is globally associated to LZ modulo approximately equal to then 1110 ZLs, if m is globally associated to R2 modulo approximately equal to then 12122 Ls, let m be the best prompt for m and cupto m and c and let x and x be fresh variables. Set m and c 12 to x2. Associate m to L x1 while computing none equal to set m and c 1111 x1. Associate m to R x2 while computing n2 equal to n if x1 f v none and n12 then n1 else n2. Figure 5. Optimize type directed normalization. Match v0 right with left v4 greater than match v0 left with left v6 greater than left right v6 greater than right right v4 greater than match v0 right with left v5 greater than left right v5 right. The result of normalizing FFF with a partial evaluator based on cupto is the residualization of the identity. Hashtag TDP cupto bool greater than bool greater than bool greater than bool ff normal equal to fun v0 greater than match v0 left with left v4 greater than match v0 right with left v6 fun v1 greater than left right v7 greater than fun v1 greater than match v1 with right v5 greater than left v2 greater than left right v3 right match v0 right with left v10 greater than fun v1 greater than match v1 with left v2 greater than right right v3 greater than left right v11 greater than fun v1 greater than right. 7 concluding remarks. We have presented a notion of normal term for the type lambda calculus with sums and prove that every term of the calculus is equivalent to 1 in normal form. Further, we have used this theoretical development as the basis to implement a partial evaluator that provides a reductionless normalization procedure for the type lambda calculus with binary sums. Our partial evaluator is in the style of TDPE, thus it can be grafted on any suitable interpreter and does not need to examine the structure of the compiled code during normalization. Its main originality is the use of the control operator set cupto to fix the relative position of abstractions and discriminators. This is the first non-trivial exploitation of the extra expressive power of set cupto over shift reset. The effectiveness of the partial evaluator has been tested on the very sophisticated terms that come from the study of isomorphisms in the type lambda calculus with sums 15 that make previously existing partial evaluators explode. The new algorithm does not use all the power of the operator set cupto. In particular, we do not use their ability to code exceptions. One could thus use only a restricted version of these operators. There is, for example, a hierarchical version of shift reset 8 that allows several but fixed levels of control. An implementation with shift reset hierarchical or not is not obvious. Acknowledgements. Thanks are due to Xavier Leroy for the call, CC for Objective Camel, and to Olivier Danvy, Andrzej Szelinsky, and Didier Remy for interesting discussions about control operators. 8 references 11D Doherty.
I think what is kind of annoying me is that, like, it seems on the code it seems a lot easier to understand how it works, and if there is examples, it's gonna be easier. But the problem is that this is already like you're kind of trapped by the language you are coding. That's kind of the thing that is annoying me. So the stuff that is not very clear is the relationship between the structure of the language and because this stuff is for creating another language following these patterns. So you're already using the built-in logic that the language has to do the comparisons and then implement the relationship between the types to create another language. But like, what does it mean? Like, what if you want to? Yeah, but I guess like it's not realistic though, because you can implement the same concepts on the language, but you are kind of trapped, I think. So essentially, what like the model that I have right now in my mind is that the language itself is going to be a topological space. So like C++ would be an object-oriented language, which forces, based on the topological space of the language, is going to force you to construct abstractions that are gonna keep you trapped on that paradigm, let's say. That's the problem. So basically, on a simplified way to say this, like C++ object-oriented programming. So if you want to implement something that is procedural or functional, you can do that, but it's gonna go against the topological structure of the language. But that's the part that I'm not 100% sure. So I guess this is the question: is like, can you use the type theory to allow you to code in a way that goes beyond the limitations of the language? I think that's the challenge. But what is kind of annoying is that probably there isn't. Like, because it's gonna be a limit. Obviously, you can implement functional programming in C++, and you can implement procedural programming in C++. But what basically, fundamentally, from first principles, what this means is that when you implement that, it's never gonna be as good as a language that is designed for functional programming. But this becomes a problem because of the osmosis of the information. So it is a very annoying thing. Because I'm thinking about from the perspective of my problem there, which I already experienced, because basically now I'm using Godot, which means I'm forced to use the engine that I have, which is built on our object-oriented paradigm. But I think that for like my situation, it's probably gonna be better to have in like this is the thing, it depends on the context. But for some situations, I think it's better to have functional programming or procedural programming. But based on the way that the engine is built and the language is built, it forces you into an object-oriented paradigm, which means you're gonna be forced to create abstractions that are overly complicated, which makes it more confusing and less efficient, which is very annoying. Because this is the core of the thing that I'm trying to see. Like from these first principles, what would be the best strategy to change this? I think that's the question. And I experienced this when doing things with C++, I think. But I wasn't sure about, like I knew there was something there, but I wasn't sure about the names. Because in some situations it seems overly complicated based on the types. Like when you're using basically templated classes and inheritance, it does feel like a lot of the times it shouldn't be that complicated. Like, there should be a simpler solution, which is very frustrating. So I'm going to open the other paper. The theory simplified. After I stream, I'm gonna search for this TPD, type directed partial evaluation.
Simple type theory simplified. Richard Southwell, December 15th, 2020. One introduction. In this document, we describe type lambda calculus with sums, except that we explicitly keep track of context and all other parts of the theory using inference rules. This is the simple type theory described in 4. This is a formalization of the type theory described in, but so that well-formed contexts and types are generated following explicit inference rules, like in the appendix of 2 of 2. The terminology is mostly taken from 3, 2 basics. An expression is a term or a type. A term is a value of a type. A term could be a constant term or a variable. Some terms are variables, as we explain later. Each term T has a set FVT of free variables, as we explain later. There are 6 kinds of expressions. 1. A typing declaration. A says that is a term of type A. 2. A universal
Yeah, I guess like this is the challenge. Like it's like how knowing this information how do you create a mental framework to improve the way you write codes given the constraints you have? And if you can, like, is it better to try to rewrite everything into another language? Or is there a way to use the language itself to build better abstractions? So basically, how to use the information to improve the way you write code on the language and understand the line. And so I guess the question is to find the line on the constraint. So what it means for how does the design of the language impact the paradigm that the code is gonna have? But I'm gonna try to clarify more because I'm not really sure if I know the right questions to ask. Yeah, I think that's I have to look into more like practical examples and study more. But I know there's something there.
Declaration A type says that A is a type. 3. An equality declaration equal to Y. A says values X and Y of type A are equal. 4. A context I is a list of typing declarations. We write IA to denote the concatenation joining of lists. 5. A context declaration. CTX is a declaration of the context I as well. Formed, the meaning will be clear later from the rules. 6. A judgment is something of the form ID where I is a context, and D is either a typing declaration or a universal declaration or an equality declaration. Sometimes we call D the declaration of the judgment ID. A rule is something of the form J1, J2, K, Jn, where J1, J2, J, and K are all judgments. The meaning of the rule is that if each judgment in J1, J2, Jn can be derived in the type theory, then judgment K may also be derived. Judgments can be stacked to make proof trees. An axiom is a rule, K, with no prerequisites. In addition to the assumed rules which we name, 3 forming base types, we write to denote the empty context. The fact that the empty context is well-formed is formalized by the rule. Empty context, CTX1. The next rule allows a well-formed context to be extended by introducing a base type A. ICTX that type base type formation. 2. The base type A must not appear in the context I. Here we assume we have some list of base types 1. If we are trying to model a particular system, we may have specific base types ready. But for now, let us just think of base types as variable types, although in this document we reserve the phrase variable for terms. So it is fine for A to be any type new to the context, 4 forming other types. This rule lets us form the unit type. ICTX, TF1 type unit formation 3. Next, product types. Cell type TB type. Thax B type product formation 4. Next, the empty type. Gamma CTX. Tho type empty formation 5. Next, sum types. 2. Thought type TB type. Thabi type. Next, function types. Sum formation 6. 5. That type TB type function formation. The B type. Forming variables. We make a variable X of type A using the following rule. That type, T, X, A, CTX context extension. Here the variable X must not appear in the context I. 7. The set of free variables of this newly made R is FVX equal to X. Also BVX equal to, where BVT denotes the set of bound variables of a term T and denotes the empty set. Judgments about variables can be formed with the following rule. T, A, a CTX, T, A memory. Reiteration. The memory rule appears as VBLE1 on page 554 of 2. The rule also appears. Inus is A. However, 10 uses a different rule which they call the identity rule instead, page 84. However, we may derive said identity rule as follows. CTX. A. Thank you empty context. XA. CTX. XAA. Base type summation. Context extermin. Memory. In category theory, memory could be thought of as projection. 5.1 about substitution. For a term U and a variable in a term A of the same type as a, we write UAX to denote the result of taking term U and replacing all free occurrences of R with term A. In such a case 5. We say that A is free for R and U if and only if no free variables of A become bound in UAX. In other words, if the intersection of FVA and BVUAR is empty. Recall that the possible bindings that happen in our system just consist of 3 cases, 1 in AX of T. We have that. 3. Each variable X in term T binds to lambda, and 2 in match is XU YV. We have that each variable X in U becomes bound, and 3 we have that in match is XU YV. We have that each variable Y in V becomes bound. To keep track of what is required within a computer, rather than just doing FEM, FE and 7 FEM, FE and etc. when terms are combined, we can form an expression tree for a term. We can also form corresponding expression trees for the free and bound variables, and when we construct UAX we replace the leaf X in U with the tree for A. Also, when we have binding operators, they color the corresponding variables which might appear within the appropriate places deeper within the expression tree, and we should make sure that after substitution. So we want to guard against previously free variables of the appropriate names, from A being there, when we replace X with A and U, so that the newly added subtree ends up lying within a colored region, involving new bindings of said variables. Maybe we should use de Bruijn notation. 6 other structural rules. Our next rules are taken from 10. Gamma A gamma, X A B B cut, gamma by X B 10. Where A is free for X and B. Is this required? Need to check about variables of chapter 1 of the way the cut rule can be visualized in terms of category theory as pictured below. Our next rule is is weakening. Gamma B B gamma A type weakening. Gamma X A B B 11. In terms of category theory, this just corresponds to doing the product of the source arrow with some other arrow, and then doing a projection before composing with the arrow. Note, after the weakening rule has been applied, some may consider the variable A to occur within B invisibly. TAYAABTI ab XYB contract 12. The picture below should how to think of contract categorically discounting I and A. When equal to, contract is LTIAIAGT, AXA-B. Our final structural rule is TAYB-ACC exchange TYB-XA-ACC 13. This allows us to think of the context as a set. Categorically exchange can be thought of as corresponding to permuting the order of objects in a product. I wonder if cut and exchange are required. 7. The other typing rules. We write FVT to denote the set of free variables of a term T. We also write BVT to denote the set of bound variables of a term T, the meaning of, which will become clear later. 7.1 Products. We describe products as negative type 7, ICTX, TF 1 unit intro 14. Here has the empty set FE equal to of free variables. Also BV equal to is the empty set. Ta TBB, TAB, AXB 5. Product intro 15. Here FE ha B equal to FEA FEB where denotes the set theoretic union. Also BV ha bi equal to BVA BVB.
Sen BPAB. GIF STPA product elementas deca exi. FOFSB F4B. Also BVFSTBB, BAB. Gen DPB, product elim theo deca epta. FOI FESNDP equal to FVP. Also BV SNP equal to BVP. 7.2 Sums. We describe sums as positive types. The following elimination rule for the empty type is like that described in 4. Gamma A type gamma E, 0 empty elim. Gamma aborta A, 18. FV aborta E equal to FVE, also BV aborta E equal to BVE. Next we have introduction rules for sum types. Sen GIA GB type. Gin laba IB sumintroenas deca enea. F bien laba FY also, BV laba BVA. Giat BBB. Giat FOD Dio.
FV in rab equal to FVB, also BV in rab equal to BVB. Gamma S, a B gamma, X AU C gamma, Y BV C sum elim. Gamma matches XUYV C21. FV matches XUYV equal to FV STFV UFVXY where L. R denotes the set of members of set A that are not in set B. Also BV matches XUYV equal to BVS BVU BVVXY. Here X.U denotes that variable X is bound to U and match XUYV, and so match XUYV binds free occurrences of X and Y. 7.3 Functions. We describe functions as negative types. Gamma X ABB, gamma lambda X AB, a B function intro 22, 6 FE X AB equal to FEBX, also BV to AAB, equal to BVBOX. Here the variable X is to bound in X a B. TFA BAA, TFA B function elim, FEFA FEFEA, also BVFA, BVF, 8 equational theory. In this section we give the rules for making equality declarations. 8.1 Equivalence relation, 8.2 Products, 23, to A reflexive, to A is symmetric, to A, equal to A to equal to A transitive. 24, 25, 26. The uniqueness principle 7 conversion rule for the unit type is TV1, teach 1 unit uniqueness. The computation rules S reduction rules for the product type are TFST AB, a product computation on TAATB, B product computation 2, TSND ABB. The uniqueness principle N conversion rule for the product types is TP, AXB, TP, FSTP, SNDP, a B product, uniqueness, 27, 28, 29, 30, 8.3 Sums. The uniqueness principle N conversion rule of the empty type 6 is the 0 FA type FR, A tabor E equal to X, A empty uniqueness. The computation rules B reduction rules for some types are 31, Ta AR, AU, CFY, BV, C sum computation 132. T-match in LB A, XUYV equal to U, A, XC, provided that A is free for X and U, TB, BAU, CFY, BVC, T-match in or BB, XUYV equal to VB, YC, provided that B is free for Y and V sum computation 233. I am guessing these freenesses conditions are required in each rule involving substitution, just like as in the internal language of a topos. Described in 5. Different variables can be used within the substitution if there are problems, as discussed in Bell's book on local set theory. The uniqueness principle and conversion rule for the sum types is TS, ABT, H, ABM, C sum uniqueness T-match S, XM in a BX, HYM in a BY, H equal to MS, C34. Provided that S, in a BR, and in a B3 all each free for H and M 8.4 functions. The computation rule 3 reduction rule for function types is TAMC T a T ax AM A equal to MAXE, provided that A is free for X and U. The uniqueness rule and conversion rule for function types is function computation 35, TF a B function uniqueness TF equal to AA, FX a B 36, provided that is provided X FVF. We also require that the same function operating on equal inputs gives equal outputs, that is, Ta BAA, a function similar inputs 37, TFA equal to FAB. 8. We also require that operating equal functions on the same input give equal outputs, that is, T A B B B function similar functions 1, TRAB equal to AX-AB, a B38. 8.5 Alpha conversion. Finally, if there is an A conversion from R E to I, AB, then we consider RBI. AB, however, a conversion is somewhat technical to implement, and I presume there is no need for a conversion if the variable names are chosen well. I guess the official rule for a conversion is T A B B F Y A B B T Y B Y X equal to B B T as a B A B, a B function alpha 39. Provided that Y is free for R and B, but I'm not sure this rule properly defines alpha conversion C8. I guess the A conversion rules corresponding to the sum type are TS A B T X A U C F Y B V C F equal to 2 A U C F X A U X, X equal to U, C T F match S X U Y V equal to match S R U, Y V C. Provided is free for X and U40. TS ABT X AU CFY BV CFY BV CFY BVY we equal to V. C T match S2 UYV equal to match S X UYV. C. Provided Y is free for Y and V9 equality implies type declaration. I propose that the following additional rule be added. Ta equal to A equal existence. 41, 42. This rule seems to make sense. Note that now we could simplify the type theory by replacing A with A equal to A throughout the theory if we want. 10 Simplified handling of types. Adding the following rules seems sensible to simplify statements of theorems. Has type 43, that type. Thax B type unformed product 1, the type 44. Thax B type unformed product 245. Thep P type. Thay B type unformed sum 146. That type. Thay B type unformed sum 247. Thep P type. Thay B type unformed function 148. That type. The B type unformed function 249. Thip type. These rules can be expressed more concisely by using Maclarty's double line notation. The following optional rule may be useful in some circumstances similar. Rules could be introduced to extract parts of terms involved in products and sums. T as a B THB B function extract. I am not sure if the above rule can be derived in this theory. In a similar way, we may also wish to include the following rules. 50. Context extract 1. ICTX. That type context extract 2. TCTX. 51. 52. Context extract 1 can be derived using has type followed by context X. Track 2. Maybe there is no need for context extract 2 because we have context extension. Avoiding bound variable clashes. Suppose we have a term B, and we wish to replace each free variable X in B with the term A. A bound variable clash will occur when there is a variable Y which is free in A but not free in B, A, X. Similar clashes can occur due to interactions with variables bound by match for some types. An example of a bound variable clash would be when term bis is A. xy, and term a is y, and the clash occurs when one considers BLA x. Bound variable clashes can be avoided by using the alpha conversion rules of subsection 8.5 to rename the variables becoming bound something new. Immediately after forming an expression with bound variables, the new names assigned to these bound variables are then considered sacred and cannot be used again. Let us look at a practical example, using lambda abstraction. The cases with match are similar. After apply the function introduction rule, TABB the AX AB AB 53, we next note that we can apply the alpha conversion rule for functions to derive that AR, AB equal to, an A, B n x, a B where n is a new sacred variable. This can be seen as follows, weakening. TX A n a B B exchange TN AX a 6B contract. Na 6n, 8 sim, function alp, TN ABN, x equal to B XB, T2XA, B equal to 2n, B, A greater than B. Now since propositionally equal terms are essentially interchangeable in our theory, we can essentially just replace AR AB with n, A, B n x, and instead implement the safe function introduction rule, TX AB B than A, B n x, a B, where the variable n is never to be used before or again. 54. Similar renaming to new unique names can be done to every bound variable and is separately for every free value of x that gets replaced with a when doing. A substitution box. However, the latter idea is perhaps a bit paranoid. I think the clashes only occur when there are free variables in some terms that have the same names as bound variables in other terms. And so provided alpha conversion is used to give new names to each newly born bound variable, the bound variable clashes will not occur. 12 consequences. 12.1 Similarity. Using equal existence to simplify, we may derive the following rule. Gamma A0 a gamma x a b b similarity. Gamma b x b0 x b 55. Where a and a 0 are both is free for x and b. The similarity rule can be proved as follows. Using the similarity rule, one may derive the following rule. Gamma fg a b a function similar functions 2. Gamma for j, using similar functions 2, transposition with function types j12. Using similar functions 2 and other previous results, we can now obtain the follows two important results about how function types work. Gamma f a b gamma x ap f x b curry. Gamma f lambda x ap a b 57. The proof of this result is as follows. Gamma x ap b gamma fx ap a b uncurry. Gamma x ap fx b 58. The proof of this result is as follows. 12.3 component-wise equal terms and products we propose. Gamma p a b gamma s to p a b s n t b equal pair. Gamma ha by p a b 59. The proof is as follows. Tria x side type a b equal to sub p t less than a b greater than equal to less than a sub p chans. Finus 6 equal to snd of vid.
Sol p8. TX at expende time sin BX BXB Shia LTX, Sado P step. Sim TLTA, SNDP FSDP, SMP, TRLTA.
P greater than. We also propose T less than 9, 6p AXB, TA a TB BFA B equal to P XB, TA equal to FSTP A. The proof is as follows. Equal first 60, 1.2, arbs DFet, AB equal to P, FS. We also propose TA a TB BAB equal to P, XB equal second 61, TB SNDP B. The proof of this is similar to that of equal first. 12.4 Universality of product. The first projection arrows is given by using product elimination rule 1, VAX B, VAX B 5 ST, A, X, Elim 1. The second projection arrow is given similarly. The notion that pairing and projection undo each other to make the red part of the diagram commute can be obtained by using product computation rules 1 and 2 with gamma equal to ZH. The uniqueness of Ha by that is, the fact that any HPAB such that FSTP equal to A and SNDP equal to B must be P equal to Ha B, can be established using equal pair with gamma equal to ZH. We can form the product FG, a B a 0 B0 using the rule, gamma F A a 0 gamma G B B0, gamma P a B HF ST GSN pi, a 0 B0 multiply functions 62, which can be proved as follows. 12.5. The many forms of judgments, the notation x1, a1, x2, a2, xn, and d can always be considered to have several equivalent meanings. We illustrate this with the following rules for 15. The n equal to 2 case. Gamma x a y b d d. Gamma lambda x a lambda b d a b d judgment to functions 63. Proof. Gamma k a b d. Gamma x a y b k x y d functions to judgment 64. Gamma k a b d. Gamma z a b k f t z s and z d functions to pair function 65. Proof. Gamma z a b d d gamma lambda x a I b z a b d h x y pair function to function 6016. Proof. Note that many of these conversions could also be performed by inline functions. For example, the isomorphism from dba and dab. 12.6 Composition. One way to express arrow composition is via the rule, gamma x a b b gamma y b gamma c composition. Gamma x a gamma b c 67, where b is free for y and gamma. Proof. So essentially the composition a b b gamma c, that is gamma b, corresponds to gamma x a gamma by c. The distributivity of composition can be established by considering how substitution works. 17. The identity arrow of b is y b y b. Hence we can see that 1 billion after a b b is b by noting that gamma x a y y b is gamma x a b b. Moreover, we can see that b gamma c after 1 billion is gamma by noting that gamma y b gamma y c is gamma y b gamma c. 12.7. Note bc can also be written as cb. The evaluation arrow cb b ec can be expressed via the rule. Universality of functions. Gamma b type, gamma c type, gamma fbc xb fx, c evaluation 68. Proof. Formation of the transpose amcb corresponds with the following special case of function introduction. Gamma x a y b m c gamma x a lambda b m b c 69. In other words, a b m c is represented as gamma x a y b m c and the transpose amcb is represented as gamma x a lambda b m b c. Moreover, a qbc is represented as gamma x a qbc and the evaluation of the composition a b e q 1 billion c is represented as gamma x a y b q y c. The fact that the diagram commutes is established as follows. The fact that any a QBC such that EQ 1 billion equal to M must be Q equal to M is established using the following special case of the Curry rule. Gamma x a q b c gamma x a y b m q y c gamma x a q lambda b m b c 70. And so this shows the universality of function types. 12.8 Universality of unit types. The arrow a1 can be established using unit introduction as follows. Gamma CTX gamma 1 gamma x a1 71. The fact that a is the only arrow from a to 1 can be established using unit uniqueness as follows. Gamma x av 1 gamma x av 172. 12.9 Universality of empty types. The presence of a function from the empty type 0 to a can be established by the following usage of the empty elimination rule. Gamma E0 A type gamma E0 E0 gamma E0 aborta a 73. 19. The fact that this arrow is unique is shown by the rule. Gamma E0 gamma E0 A type gamma E0 A gamma E0 aborta a empty uniqueness 74. 12.10 Universality of sum types. The fact that a B match C makes the following diagram commute is established by sum computation 1 and sum computation 2. The fact that a B match C is the unique arrow from a B to C with this property is established by some uniqueness. In particular, the fact can be established by using the alpha conversion principle of sum types, together with the uniqueness principle with sum types, as I discuss in my video foundations, simple type theory. 13 Further directions. 1. It would be good to show that we can prove all the categorical machinery, terminal object, products, initial object, coproducts, exponential objects, can be produced, and that rules expressing their universal properties can be derived. 2. If we code up the above theory, we just seem to have to keep track of Dependencies like how B depends on A and B, and some label, and the lists of free and bound variables and which type a term has. We could imagine all this as part of the data structure of the term, and then terms start to look a lot more like objects in a category of presheaves, or like algebra's W-types. This suggests we could abstract this theory, and open up the possibility of categorical analysis of the meta-theory. 3. We may want to add natural number types like in 9. 20. 4. We may want to add equalizers, subobject classifiers and reference to monomorphisms, so we can do topos theory. 5. The theory above allows us to model any bicartesian closed category. We can model cat by adding appropriate axioms as described in 5.6. If equalizers can be included, we can represent monomorphisms by the property that pulling them back along themselves gives the identity, and hence we can include rules for subobject classifiers, and we can model topos theory. We could also add the rule about pointwise equal arrows being equal to model set. Here are some extra notes about things I want to elaborate on in this simple type theory distributivity, an alternative interpretation of entailment notation function composition converting between A before Christ and A x BC, universality of function types, universality of initial, terminal and coproduct points. Terminal objects and elements raising arrows to powers lovers lambda do example of making an element of 1 times a read how substitution is treated prove exponential properties. Maybe we should use Bruggen notation. Should we also add the idea that equal things can replace for each other, like we can get from McLarty-Bell? Oh wait, answer add proofs finish exponentials note cut seems optional add equalizer game show product universality show exponential universality. References. 1. Extensional normalization and type-directed partial evaluation for typed lambda calculus with sums Vincent Ballot. Roberto Di Cosmo Marcello. Fiore. 2. Homotopy type theory book. 3. In CATLAB type theory page in CATLAB type theory. 4. Video. A K7 GSRY5 elementary categories. Elementary to poses Colin McLarty's 6 Stack Exchange website Math Stack Exchange 7 NeetLab products product types. Functional Pearls alpha conversion is easy Thorsten Altenkirch. 9. Introduction to higher order categorical logic Lambeck and Scott 10 Practical Foundations of Mathematics. Chapter 2 Paul Taylor.
Actually, I'm going to stop streaming here. I think last thing I'm gonna do is just search for an example. Interesting. So is it written in Haskell? So I'm gonna already watched a couple of videos on Haskell, but I think I'm gonna have to learn Haskell actually, because there's a bunch of papers that I got as well from calculating compilers from a guy, I think his name is Graham or whatever, and I, most of the papers, or if not all the papers, are like they talk about in terms of Haskell, and I think Haskell is used a lot for compilers. So I'm probably gonna have to learn this. I'm gonna download this stuff here.
Navigation menu. You signed in with another tab or window. To refresh. This compiler can lower a type theoretic lambda calculus into efficient LLVM code. Each expression is strictly evaluated, and functions are called by value. The languages provide primitives for pointers, arrays, and C strings. It even includes stack and heap management and allows for mutation and unchecked side effects. These are dangerous, but the theories provided are intended as compiler targets for more advanced theories which can type check on usages and side effects. So far, the theories provided are simply type lambda calculus, STLC, and system. This code is in active development, and many features are unimplemented. In the future, we hope to have a dependent type theory of some kind, which is capable of checking resource usage. The current candidate theory is quantitative type theory, QTT. Another subject of interest is laziness. We may look into an alternate backend which will compile to lazy garbage collected code. Linear languages may also be a possible future target. Currently, it's not clear how languages should interact. Requirements. You will need LLVM8 and the latest GHC Cabal for compiling Haskell. Also, you should run Cabal update to ensure you have the freshest set of packages for Haskell. Running tests. To run tests, run the command Cabal new test TTC golden. Building files. Currently only .tlc. Files are supported. To build files, use the command Cabal new run TTC out file in file. If the build succeeds, you may execute the out file. The default out file is a out. Languages. We have a family of languages. LLTT, low-level type theory, a calculus that easily compiles to LLVM code. STLC, simply type lambda calculus. System, STLC type variables, and polymorphism. Useful links. Some links to help with development. Parsing. www.haskell.org/alex/doc/html/index.html. www.haskell.org/happy/doc/html. Pattern matching compiler. llang.org/blog/compiling pattern matching/lvm.http package.haskell.org/package/lvmhs pure. https mapping high level constructs to lvmir.redocs.io and latest redme.html. Destination passing style. www.microsoft.com/nus
Yeah, it's everything in Haskell. So I'm gonna learn the basics of Haskell, and then probably next time I'm going to study this stuff here. I have to watch a bunch of stuff as well. But I think next time we're gonna go over this code here. So I'm gonna do basically what I did today. So go over some examples on assembly, and then spend the rest of the time trying to understand, because looking into the actual implementation is gonna help a lot to create a connection between the theory and the practice.
Where can I find a code implementation of type-directed partial evaluation without let insertion TPD? You can find code implementations related to type-directed partial evaluation without let insertion TPD in the context of type theory and compilers primarily on GitHub. Here are some notable resources. Type Theory Compiler. This repository contains a compiler that lowers type theoretic lambda calculus into efficient LLVM IR code. It supports various languages, including simply typed lambda calculus, STLC, and system, which are relevant for exploring TPD concepts. The project is still in active development, aiming to incorporate more advanced theories, including dependent types in the future. You can explore the code and its architecture at Type Theory Compiler 1. Research papers and articles, while not direct implementations, research papers often discuss TPD and its applications in type theory. These documents can provide theoretical foundations and potential algorithms that can be implemented in code. For example, understanding how type inference works in languages like Haskell or OCaml can be beneficial since they utilize similar principles. Type ADB fundamentals. This resource discusses how type theory underpins various programming paradigms, including functional programming. Although it does not provide direct code implementations, it offers insights into how TPD could be applied within type systems 5. Community discussions. Platforms like Reddit may have discussions or links to projects that explore TPD concepts and practical scenarios. Engaging with these communities can lead to discovering additional resources or implementations shared by other developers. For practical implementation, you may need to adapt existing code from the type theory compiler or related projects while considering the specific requirements of TPD in your context. Are there any specific libraries or frameworks that support TPD in type theory? How does TPD differ from traditional partial evaluation in compilers? Can you provide examples of TPD?
So probably next time I'm gonna have to go over like learn Haskell as I go over this stuff here. And I'm probably not gonna be able to, because I assume that what is gonna happen is that there's gonna be a bunch of problems to set everything up. And I already seen that it's very annoying to set things up for Haskell. So I'm probably gonna try to spend some time trying to figure this out on stream, but if I can't figure out, then I'm just gonna go look into the source code and then read the documentation to ask questions about stuff that I don't understand. And I'm probably going to start with the simplest one. Yeah, it's probably gonna be this one. Then from this one I study this one, and then I study this one. So see you next time.